Go with
live on the internet.
Live. Hey, we're live on the internet.
Tom, I know this is your first time on the internet.
Yeah.
So glad.
Hi, interweb.
Yeah. When was the first time you went live?
Ooh.
Do you remember?
You've
made a lot of videos.
I have done a lot of videos. I remember back in the day at NVIDIA, probably about 2009, we started doing our first videos. And, you know, they have a whole team that does videos now, and they always did. And there's a guy, Ray and Steve used to do this for us. And I remember I became one of our first big videos. It had 1 million views.
Oh, wow.
And I did, and we just started playing with social media at that time, and we're like, we should get somebody to like focus on this shit. So I did a video where I sneak peeked like a 580 or something like that, and you can see the video went kind of crazy and viral, and we thought it was the biggest thing ever. It was our biggest video ever at 1 million views. So,
nice.
And it always starts with like some guys locked in a disused closet, basically.
This was I think Steve came up with a camera to my cube, and so it's literally me in my cube. And I did a quick history lesson, like walking through older GPUs I had just scattered around. And
is that video still live? Do you know?
I think it is.
Oh, that's cool. Well, speaking of live, we're here live on the internet. Welcome everybody. This is the pre-show, arguably the best part of the Full Nerd. We will talk about GPU topics, CPU topics, Intel topics. We have an Intel fellow here, Tom Petersen. Lots of good chat, but this is just the pre-show. We're getting things warmed up, making sure all the hamsters are running. Tom, we have the first question in for the pre-show.
Nice.
Friend of the show, Brian VS. Have you ever found a USB drive on the floor at work?
That's an excellent question. I have not, and if I did, I would not use it.
Why not?
Well, because
what if it's like a
Stux virus,
a terabyte?
Stux virus. Plus, I think it's because there's I don't really know the last time I used a USB key. Because everything is now web.
In the cloud.
It's in the cloud, right? And I've got all kinds of terabytes of storage in the cloud. So USB keys for me are kind of like floppy drives now.
Wow.
Well,
don't use them.
It's like you use it when you need to install Windows or Linux or something.
You used to, yeah. But I have some old photos that are actually on a CD-ROM, and I'm like, how do you get that? I had to go buy an external CD-ROM drive so that I could download my photos and put them on my interweb.
Up in the cloud. Somewhere up there.
The number of people making optical drives for PCs it's down to one now.
Is that
my
right?
understanding is LG
I'm not
is
surprised.
kind of still making them. Maybe we think they haven't said they're not anymore.
I'm not surprised.
Yeah,
they're kind of done.
Yeah,
and I think USB drives are kind of heading that way, but not done yet.
Okay, I've got a 2 terabyte drive right here.
Do you really?
And
what do you use? Do you transfer data?
Okay,
on that?
hold on. Let me.
Oh, here it comes.
Yeah, so I actually have a little satchel. This is all not all USB keys.
Oh my God!
Your corporate security person is screaming.
Yeah.
Right now,
so this drive specifically is full of like projects we're working on.
Okay.
So like that kind of stuff. This is for updating BIOSes. So it's my FAT32 drive.
I like it.
And whatever, it's just junk. This is my Windows 11 24H2 install drive because 25H2 disables some of the local account stuff. So I hold on to a
So this is
drive.
A good version of Windows.
Yes, it's a good version.
Maybe the last good version of Windows, Tom.
This is Ventoy, so this is where I put all my Linux installs.
Oh. You could also put that 24H2 on there,
Well, I do also have it on there, but I like having this around that I can put on the shelf.
Yeah, that's
if I ever need a bust in case of emergency.
Yeah.
And then this one is all of my benchmark stuff for benchmarking.
Do you have an app that is your benchmark app? You just put in and you click go and it just does everything?
That would be nice. That sounds really good.
You don't have that.
No. Listen, I don't know if did you ever meet Gordon Maung? He was handmade farm to table benchmarks. He was horribly against any sort of automation. So I have never learned anything about automation.
I didn't know he was against automation.
Oh, we talked about it all the time.
Wow.
Yeah. Cool, because Dr. Ian Cutcher's Tech Potato would show up and he'd be like, "Oh yeah, no, I have a script that just runs everything for 24 hours, and then I'll come back afterward and it's all done." And Gordon was like, "Nope, I need to feel it."
Well, he's like, "You have to watch it.
You got to watch it. You got to feel it.
Okay.
You got to feel the heat coming off.
Okay.
You got to feel the frustration when something breaks.
I get it. Back in the day, there was some competition between some of these GPU vendors and the green guys and the red guys. Yeah, that's what I say. Back in the day, before the game was won, effectively.
Yeah.
And it would be very important to get access to hardware as soon as it became available, right? Because you got to know where you are. Mm-hmm. And so some of these companies developed USB drives that you could send around the world that would land in systems that would generate reports and send them home.
Wow.
Yeah.
Oh,
Yeah.
okay. Well, that's
Dark
nice.
business.
So and then sometimes somebody would leave that drive somewhere for somebody to pick
I'm
it up.
just saying, there's like the information, especially in an industry as highly charged as this, is super critical. And benchmarks, synthetic benchmarks, live benchmarks, are super important. So you can imagine that automation and like internet and webs and all that kind of stuff is a big thing. Yeah.
Interesting.
Yeah.
Yeah.
Wow.
No, that is fun.
Wow.
We're going to talk about a lot of fun stuff on the show today. I mean, we don't have to talk about stuff.
Whatever.
Yeah.
I'm ready.
It could just be boring stuff we want. Willis, how are things going on the hamster cages?
I'm getting some.
Exploding glass in the kitchen I'd never considered before. I was expecting like a Leidenfrost effect. It's skating across the top of the counter.
I had no
really
idea.
Fun.
I had no idea that it was possible, but it turns out.
You know, there's two kinds of Pyrex. There's old Pyrex and new Pyrex.
I didn't know this.
So there's a whole market in pre-90s Pyrex because they changed the composition of the soda glass and like.
Does the old which one
The old one is better. The new one explodes. Okay. So there's look, this is what happens. All the good material scientists either go into like computer engineering and like aerospace stuff or hair products. And now there's nobody left for glass.
Nobody
anymore.
knows how to not make blowing up glass anymore.
Exactly. It turns out just all of it goes to Apple.
Speaking of blowing stuff up,
how's it going?
OBS, yeah.
We blew the hamster wheel.
Yeah, the hamster wheels are blown up now. We should be good.
This
is why we
do a pre-show.
Yeah. Well, I think it's also the Focusrite driver.
Oh no!
So
Test,
we need
everyone.
Anyway, I think we're back. Thumbs up. Everyone give a thumbs up in the chat. Give a thumbs up for Tom.
Heart,
Hey, no. For all of us, for the
coming.
team.
Yeah, for the team. Yeah, we'll see. Thumbs up to Brad.
Liquid R in the chat knows about the Pyrex, though. The old one was borosilicate. The new one is soda lime.
Okay, thumbs up in the chat. We got thumbs up. I think we should just get going.
Let's do it.
I love how you can tune into the full nerd and the hamster wheels are broken, so we just get nerdy about Pyrex.
Yeah.
And
I mean, believe me, this day's been a day.
Welcome to Glass Talk.
Yeah,
I almost didn't get here because of your fire drill.
Yeah.
And
we had a
congratulations
literal
on the
fire
whistle,
drill.
by the way. You are the floor.
I'm the floor warden. Yeah, or one of the floor wardens. I'm for our company. I had to yell some people because they weren't evacuating all the way to the evacuation.
They were in the bathroom.
I bet you
there was a guy in the bathroom, but then people were gathering outside of the building right out back, and I was like, no, we have a dedicated, and they're like, it's just a drill. I don't care. That's
why I have the whistle.
Yeah.
Don't
Do you have a whistle? You don't have a whistle. I have a whistle. Get out as safely.
Yeah, I understand.
Anyway, all right, Willis.
Yes, we are.
How you doing over there, man? We'll get you a nice lunch.
It's been a stressful day. Hey, everyone. We're ready to roll. Let's
cool.
do this.
Brad, you ready to roll?
Born ready.
All right, cool. Born ready. I like it. Then let's go. We have an intro to get to. You ready?
Yep, let's do it.
In this episode of The Full Nerd, we talked to Tom Petersen about Panther Lake, Xe3, Celestial, all that fun stuff right now. Come up that way, fly.
Good stuff.
And welcome everyone to episode 370 of the Full Nerd Podcast, PC World's premier podcast about PC building news. I am your fill-in host, Adam Patrick Murray, but I am not alone. I am with a whole bunch of people. Here on the line, first I'll get to, is one co-host, Brad Charkis. Hello, Brad.
Hello, I'm on the line.
And also beat me really good in fantasy football this week. That's fine. We don't need to get to that. At the table here, we got one Will Smith.
Oh,
hello, Will.
Hello.
You're on the corner over there.
Yeah, my
Is it
normal
comfortable?
position.
Yeah.
I feel weird. I feel like I'm looking at the wrong side. Usually I get the good side, but today I have the other side of Adam. I have the party side.
My part's the good side.
Oh, the part's okay.
Yeah. Speaking of the good side, somebody who has all good sides is one Tom Petersen, a fellow at Intel.
Yes. It's great to be back.
Yeah. Here in the studio, really appreciate you coming on.
Thank you, Adam.
We're going to talk about a lot of cool stuff, but first I want to thank our amazing producer, Willis Lai, for holding in there.
Good job.
Controlling the verticals and horizontals.
Hey, everyone. Thanks for putting up with us. We had some technical difficulties. It is a Tuesday after all, so yeah, thanks, everyone.
Yeah.
Thanks, Tom, for coming.
I'm glad to be here. I had a great night in San Francisco last night, so it's fun. I'm ready to go.
Well, but you're local to the Bay.
I am.
Yeah.
I live in San Jose, so I just drove up.
It's not an easy drive.
It's like one of the 3 days in San Francisco that it's beautiful weather, right? It's not too hot, not too cold, not foggy. It's crazy.
Yeah, I went camping this weekend in the Presidio.
Wow.
Which, there's a little campground in the Presidio for groups.
That.
Yeah.
Really?
And it was the best weather we've ever had in San Francisco.
It's beautiful.
We went for a sunset walk. We could see the water. There was no fog. It was not too hot. It was not too cold. It was beautiful.
It is incredible.
Well, you know what? I have a hard time seeing through the fog ahead to Panther Lake.
Ooh, yes.
Wow. Panther Lake is nebulous. It's out there. We went to the tech tour. Will and I and Mark Hawkman went to the tech tour talking about Panther Lake. Talked about the server stuff too, but we don't cover the server stuff too much. So we're just going to focus on consumer here. You gave a number of presentations.
I did. I talked a lot.
Not only about CPU or about the GPU. You talked about the NPU. You talked about gaming, low power gaming. AI, yeah. So we're here to talk about AI the whole time. Everybody loves AI.
I know.
Yeah, but it was interesting leading up to the tech tour, which was planned months in advance. There was news that dropped of, hey, Lip Bouton, the CEO of Intel, got on a call with the CEO of NVIDIA, talked a little bit about Sherry, and then talked a little bit about having a partnership between the two companies.
They did. I heard the Sherry line.
Yeah. I mean, who doesn't like Sherry?
Yeah. Was it Sherry or Brandy? I don't know.
I thought it was.
I thought it was Brandy.
Brandy.
She's a fine girl. Whatever.
Okay.
Old Louis Vuitton.
Yeah. So.
They weren't talking about borosilicate glass. That's what I know.
Oh, that's good. Or Pyrex.
Yeah.
No.
So what can you talk about?
Well, obviously, it's a partnership between NVIDIA and Intel, and I think they announced that there's going to be two halves of the deal. One is that NVIDIA is integrating for data center type applications, and so CPUs going to NVIDIA for integrated products coming from NVIDIA for data center, and also we announced that tiles of GPUs are coming from NVIDIA to some of our consumer SoCs.
So it means presumably at some point in the future, we'll be able to buy a consumer CPU that has that we can choose between Intel or NVIDIA.
I believe
GPUs
that is
on
the
it.
intention, and it depends on the segment that you're talking about. So if you think about it, I think this is just back to that integration always wins argument that I've heard for many, many years, and that's kind of Intel's strategy over the decades. Over time, the economics of integration become overwhelming. And that means that you can more cheaply produce the same amount of silicon by putting it closer and closer together without all the interconnects, without all the drivers, without all the large PHYs. And so it seems to me that it's inevitable that this is the next step. And chiplets, which is this idea of constructing larger SoCs through multiple smaller chiplets, is the enabling technology. And advanced packaging, which is also something Intel's leading in, is what's driving all of this. It's almost like, I don't know what the right word is. It's disaggregated SoC construction, but now it's sort of like multi-vendor disaggregated SoC construction, and that's a new thing.
I mean, this isn't necessarily the first time there was a NUC that had the KB Lake S, with an AMD GPU.
Yep.
So I mean,
don't get me wrong. It's not as simple as, hey, there's a chip and we're just going to stick it next to our CPU. You got to get into like what's an optimal way to do that, because there's an interface between our chiplets, meaning the chiplets that we make for graphics, and our CPUs, and that interface is something that's proprietary to Intel. So now it's not PCI Express, because you wouldn't want to have that big, beefy, complex interface between two chiplets. You want something more optimal. So all of that has to get worked out with, is there some kind of emerging industry standard that you would do? Is it going to be a proprietary thing? I think all of these are just questions that are not yet resolved, and that's the beginning of this partnership.
And is there a foundry component to this as well, where potentially new foundries are accessible to NVIDIA?
I do not know.
Okay.
I'm not close enough to the foundry stuff to talk intelligently, but I know that we are very interested in leveraging our foundry technology across all different IHVs. So I would hope that someday they would use our foundry, but again, I'm not an expert there.
Okay.
Well, no, I think the biggest thing to come out of this, correct me if I'm wrong, you guys, but a lot of people are like, okay, well, what does this mean for the Intel graphics division? Does this mean that, now they're going to work with AMT? They don't need NVIDIA. They don't need dedicated graphics or anything like that. What does it mean?
I don't think it's understood yet. I would expect Intel to continue to develop graphics IP for the long term. And the reason I say that is because there's times when, you want a smaller, more power efficient IP, and there's times when you want a larger, more complex IP. Maybe there are like multiple different segments. Ignoring all the consumer stuff, which I do expect us to continue to do, there's also data center designs. And we just announced our brand new Xe3P architecture going into a data center GPU. And that's all part of one great big IP enabling effort that we do. So think of it as we've got a core of IP design for graphics, which is Xe3, Xe3P, and whatever comes after that. That core can go into multiple different market SoCs, like one for data center or one for other types of applications. And I don't think we're walking away from that.
Well, I think that's what a lot of people, I feel like, forget in this announcement. A lot of people who listen to this are gamers, right? All they care about is gaming, and so I'm sure there's going to be a big component of it that is data center.
Yep.
And so that makes sense. But then, when you're talking about the consumer space, you're talking about being able to feed everything from real thin and light laptops to maybe big gaming laptops.
Absolutely.
and in between.
And again, it's this. Today, discrete GPUs are in laptops are an external device that is effectively connected through PCI Express, right? That's the way it works today. And the next step forward in that sort of design evolution is to become more closely coupled, more specialized on the interfaces to get both better power, better performance, and more low cost. So I kind of view it as it's not surprising, because integration is needed to continue to move up the performance curve while not raising power and lowering costs.
I was going to say there's also a real benefit to having everything in the same package from a like a thermal and packaging and design standpoint for a laptop, right?
There is, and reliability as well. Once you get into the world of advanced packaging, you can do subcomponent testing and you can improve overall yields, and then it's much more physically stable. So there's lots of good reasons why integration always wins.
Okay. Well, I do want to talk about naming. So I think maybe this is the first time we'll bring up a.
We'll try to bring up a slide.
Tap has brought some of the slides. We're not going to go through the whole presentation, but we are going to show off some key points.
You want to do naming first?
Let's do naming first because you touched on it.
Okay.
Actually, sorry, I got the feed not coming in right now.
For the maybe unplug and replug the.
Unplug and replug.
Oh, there. Oh, it did fallen out. I think.
Good.
And
wait a second. Stand by.
I had it for a second.
All right, stand by.
Presentation mode, for all the audio listeners, we're doing a little bit of troubleshooting for the slides.
No, there it is.
There it is. Okay.
All right, coming in.
So we have some slides.
Yes.
The first one, if you want to bring it up, Willis, is kind of showing the GPU product family roadmap.
Yes.
Now, back in the day, there existed discrete Arc. At the beginning of time,
Yes.
Alchemist
Intel
was
Arc
a thing.
A series was
Yeah.
first.
Do you remember those days?
I do.
I
I do. That was beautiful days.
That was
a lot of
big
engineers
time.
broke their picks making that first discrete GPU. A lot of hard work and resulted in a pretty darn good product with Alchemist. It's our very first time.
And that was XE.
That was XE architecture. Lots of variants. If you remember in the beginning, we had sub-named every segment. So it was letter soup. And as I reflected upon that, I said, I don't think this is adding any value. At the end of the day, the naming for our architectures is just too complicated. Let's simplify that. So simplifying that gets you to saying, now there are multiple things that are just XE, right? But when we launched them, they all had different names. But now there's
Could I ask a quick question?
Yes,
here?
of course, Brad.
One of the questions I was going to ask, when Alchemist came out, there was talk about XP, HPG, and LG.
Yes.
Is that still a thing?
It's just variants of the XE architecture. Now, I think if you look in documents and you look in drivers, you might find sort of like fragments in the Linux driver. But from all intents and purposes, XE is a very common sort of tree of the architecture, and all the variants are just like derivatives. They're all slightly different, which is another big learning that we have, is that you really can't afford to have lots of derivatives of architectures and like one derivative of the architecture per chip that does not scale. So having a base architecture that is stable, that you then have compromises as you move to SoCs is probably the better strategy.
So what kind of stuff changes inside those architectures, I guess?
It's things like memory interfaces. Like if you're an IP going towards discrete GPUs, you have a totally different memory subsystem versus an IP going to an integrated GPU. It's also things like XE counts, core counts. But the problem that I think we had to learn is that engineers engineer. So we've got a bunch of engineers that are looking at all the stuff that they wish they hadn't done when they did the first version of the architecture, and they're making tiny little changes to the architecture, and they're making tiny little changes that all get wrapped up into that XE3 HPG, which is 6 months later. Now, if you're a product planner, would you have said, fix all the things as you go along in architecture? Maybe, but you might just say, save all those up, and then we're going to do those in our next big architecture. So it's like fragmenting the architecture a little bit because you're improving it with time rather than waiting for generational changes. And I think that in the future, we will probably be much more rigorous about the architecture that we launch is the architecture. It's called XE3, and it's not going to change. And then the next one we do is called XE4, or XE3P in this case, and that will have significant changes. Less of this like sort of like lots of small changes everywhere, because it's a verification nightmare. And so I think that's what you're going to see a little bit more in the naming.
And a confusion for the consumer side.
Yeah.
Like, I mean, we have Robert Lawrence, friend of the show, says, I get confused by all the lakes. And
Yeah.
it's like you have Series 200 CPUs, which are both
Yes.
Arrow Lake and Lunar Lake,
Yes.
but one has XE1, one has XE2.
It's very confusing.
Yeah,
It
so I mean, it's complicated. So you're trying to help decode it?
I'm trying to help decode it here a little bit. So on the top line, that's the major architecture family, and that's things like what's the software model? How does this look like to most developers? And that's why you'll see Arc A series, which was our Alchemist discrete GPU and also our notebook GPUs, and then you'll see Meteor Lake and I think that's Arrow Lake that are all XE architecture, right? Now, unfortunately, we didn't have a future view of all the names of everything we were going to need, so that's why you see the Intel Arc graphics. So you can see there's a naming change. That's the product name that changes sort of in the middle of the A series. And we actually carried that naming scheme over into XE2 with Lunar Lake. So the bottom line is kind of like late binding decisions that our go-to-market teams are making based on what do they see in the market, what do they believe will help communicate the most clearly about the product, and they're also trying to simplify things. So everybody's got good goals, but the problem is that these naming decisions are happening at very different times. So that's why you see things sort of get a little complicated as you go down this stack. But nevertheless, having the physical product in the middle is the thing that we're selling, and then the thing that it is built on is on top, which is the architecture, and the thing that it's called is on the bottom.
But now you have a new one.
Now I have a new one too.
XE3, and
it's going to simplify things.
It's going to make it all easier.
And
yes,
it's Celestial, right?
No, it's actually not.
It's the third one. A, B, C.
A, B. Yeah. So
okay.
Again, I think again this is one of those. If we had the crystal ball to look forward. XE3 got named a long time ago, right? Now XE3 is sort of like, think of it as mostly similar to XE2. The things that I talk about that are changing are important, but it's more evolutionary off of XE2. And if you were completely transparently like naming these things, you probably would have called it XE2 Prime or XE2 plus plus or something like that, right?
Plus.
But put a 1 after it, right?
But unfortunately that XE3 name got decided years ago. And it's Damian told me it's actually spread around the Linux stack. So if you look around Linux code, you'll see XE3 in there. So changing the name of that would have been very, very painful. So that's why you're kind of seeing this disjointness about Intel Arc B series. Well, it's B series because it's similar to XE2, right? And we want to be transparent with our customers. Panther Lake has a new and improved GPU, but that GPU is bigger and it's very similar architecture to B series.
So where does the driver division happen? Are these all running the same driver?
It's a unified driver.
Okay.
Yeah.
But
so the driver has to know about all these variants.
Okay, but internally it's the same. It's one driver stack all the way through.
Yeah,
okay.
One driver.
Which I mean is also something that's been different and had to be ironed out with the launch of Alchemist.
And you will see branches that occur when we launch products that this driver has all the bug fixes for this thing, but they come back together.
Okay.
Because the architecture is unified and it supports all of our GPUs back to some old time.
Yeah, actually I still get some laptops in for testing that have the old command center, and then when I do the updates, the new graphics software pops up and is like, hey, by the way, you have this legacy thing, you should probably delete
that thing. Yeah, that's my fault, but that's a whole nother story.
Okay, well, all right,
so then
well, last year you came on this podcast, you sat at this table, you said, hey, listen, the team behind Celestial, they're done.
Yes.
They're done. They're moving on to something else. So now we're starting to see the work that they did.
Yeah. What I said was the architecture team is done.
Yeah, for Celestial.
The next big architecture, they're already done. And they are. And this is the first instance of a lot of the work they did, XE3P. But you'll also see there's another clicker I'm going to give you, XE3P, which we also just announced.
Oh, so that's Celestial. So that's discrete.
It's the next one. And that is first going to appear, and we already announced a design using that, which is a data center design. So
okay, so this is actually something new to us. This wasn't talked about during the tech tour. It was just kind of shown off. But
we had it there, but we knew that we were going to be announcing it a couple weeks later, and we didn't want you to be like, why was there no XE3P? So we put it on here, but we didn't really talk about it because we're here to talk about primarily XE3.
Yeah, I mean, I think a lot of people did think that, oh, well, that's Celestial. That's the next discrete GPU.
Yeah.
That is not the next discrete GPU.
I try not to talk about future unreleased products. Okay. So from my perspective, I know that we've announced an XE3P architecture, and that is a more substantially different architecture than XE3 was versus XE2. So think about XE3 as our big bite.
And this is codename Crescent Island.
Crescent
if somebody
Island.
wants to
Crescent
look
Island.
it up.
Yeah, go ahead and look it up.
I don't know if Brad did we do any news pieces about this?
No, we did not.
Okay, I'm seeing a couple news. Yeah, I'm seeing a couple news pieces around.
Yeah,
the interwebs
it's a
by
pretty
this.
exciting thing for us because it is an inference only data center product, and that market is just enormous.
Yeah.
So if you can provide a competitive advantage in inference, that could be a very, very good thing.
I mean, but this thing's got to do good at gaming too, though, right?
The architecture definitely does have gaming capabilities. Yes.
Yeah, will it run Crisis? That's really the only thing
Will
I
it
care
run
about.
Crisis? I don't know. I assume so.
I mean, it's got 160 gigs of LPDDR5X memory support.
Yes, it's pretty
up
big.
to
Pretty big memory.
Yeah, that's a big die. Have you seen it physically?
I have not seen the die physically, but that memory, it's a big data center card.
It's like a big full length.
Yeah.
Full length.
Do you know what the P stands for?
Plus.
Okay.
Damian told me that. Damian, is that
okay,
true?
that's
Hey,
good.
Damian, you should be in the chat. I think it's plus. I'm gonna. We actually had that question. Is it plus?
Okay. Yeah. So we're getting back to plus.
Yes.
Yeah.
Okay.
Yes, but this one.
Since we're talking about like brand names, almost B series, A series, C series, and unannounced products, since you guys didn't name this Celestial XE3, is there a chance still that we could still see a B770 desktop card?
Well, Brad, as you know, I don't talk about unreleased products, and I try not to hint either. And the reason I don't is because things change, and anything that I say now is just my best guess. So I decline to participate in that speculation, my friend.
I figured you would, but I had to shoot a shot.
I think the issue though is that on this slide there's no more room for a Celestial if it comes out.
Yeah, we would need a new slide.
Yeah, you need a new slide.
You would definitely need a new slide. And if it was, but it's going to be more, whatever that color is, purple, pink. Pinky.
I assume if there's a new slide, the numbers are going to iterate. All rules are out. Anything can
Roll
happen.
the dice, baby.
Yeah.
Anything can happen.
So Celestial could be XE4.
It could be XE6. We don't know, right?
Yeah.
I mean, look, it's worked before. When the Xbox 360 came out, the next one wasn't the 720. It was the Xbox
360.
One.
Yeah.
It just went
the
back to
one.
one.
Yeah, they went all the way
And
full circle.
this has happened over the decades of GPUs as well, right?
We've seen them loop around.
Yeah, they do loop around. Like, what is going to happen? Like, I think it was 1080, 2080. Oh, it's still in the thousands, right? It's 780, 7080.
Yeah.
80. They won't do it. Probably won't do an 8080. But what do? You're going to do a 10,000?
No, nobody wants a 10,000.
No, you're going to go back to
No.
1, 2,
Look,
3.
This Dell laptop I have is a Model 9350. It's an XPS 13 9350. There's also a 9350 from like 10 years ago.
Yes.
Also
Yes.
a Dell XPS 13.
I will mention though,
Everything
we're in good space on our architecture names, right? Because we are only at 3.
Yeah. You have roughly 23
got more
letters
to
to
go.
go.
We have a
Listen,
life.
here we go. Somebody said this in the chat. I have a solution for this.
Oh no, here it comes.
You could just get a decoder wheel. You know,
Oh my God.
Team Red has this decoder wheel that they came out with.
Oh,
You know,
wow.
you're just like, okay, what's the architecture family? What's the model number?
Yeah.
And what's the power state? There you go. You know.
Oh, I get it.
So maybe the
something like that.
GPU division needs a decoder wheel.
Well, maybe. I think the CPU division we could use for some of that. I feel like the names on the CPU side are getting more rational, I think, over time.
I mean, look, this is a conversation that we've been having since the early 2000s or probably before.
Yeah.
But I remember sitting in a room with a bunch of NVIDIA executives who were like, we really like the way Germans name their cars. We're gonna start. The first number is gonna mean the class,
Yes.
and the second one's gonna mean the performance tier, and the
Yes.
third one's gonna mean the trim or
the
something,
variation,
and then the last one's always gonna be a 0, and then that lasted like 2 generations.
Yeah, especially with the 285. I don't remember.
Yeah.
The 285.
Yeah.
That's hilarious because the whole idea was that the last one was going to be 0, and it got busted like 2 years later.
It was literally
Yeah.
mid-cycle refresh, I think. Yeah.
Yeah. Okay. Well, that's naming.
All right. And I'm very excited about it because XE3 drives Panther Lake. And XE3 is a nice improvement over XE2, and it delivers great performance and per watt. There you go, plug.
I think I have a question that's a good follow-up to that.
Go,
I'm
Brad.
glad that you mentioned this is kind of like XE 2.5, 2.5 plus, whatever you would.
Yeah.
Because that's kind of the impression I had going through all the stuff. Some of the concerns with Battle Mage and Arc were CPU overhead, were, not full utilization. It feels like a lot of the changes here are designed to directly combat that.
Oh,
I was wondering
absolutely.
if you could just talk about some of that.
Yeah,
I think
absolutely,
it's
Brad.
important
Yeah, that's a really good question. You know, this gets into a tough topic where you're saying, when you have low utilization of your hardware compute engine, that's a problem because you're paying for it. It's designed to have higher performance, and the power that it's generating is kind of higher because it wants to be running math, but it's not. So when you have that happen, you could either say, I have a software problem because the software is not like tuned to work for the hardware that you have, or you could say I have a hardware problem because the hardware has bugs that are causing the software not to run as nicely as it should, or we have to do workarounds for hardware bugs. Or it could be an architecture problem. It could be that we didn't have a thing that we need, and the pipeline itself just gets kind of choked up in general. So I think when you look at XE3, it's an architectural improvement that fixes some things that could not be addressed in software. But in parallel, we're always doing software improvements. So Brad, I don't know if you saw, but our CPU utilization is now much lower on Battlemage than it used to be, and that's 100% software. And so we're kind of, think of it as every time it's not perfect, you could fix it by doing an architectural change. You can usually fix it by doing things like SKU changes, configuration changes. But you can almost always fix it with software. But if you're fixing bugs and fixing performance problems with software, you're not working on other things that you would like to be working on. So all of these things are very complicated changes. Clearly, XE3 is a big step forward in terms of efficiency for us, and it does correct a lot of the sort of micro architectural defects that we wish we had done in the original XE2 architecture.
And you have a couple slides. I want to get to one of them where you talk about the actual micro benchmarks.
Okay.
Because I thought this was interesting when you showed it, because I mean we're all familiar with benchmarking something at the point of release when it's done. You and your team need to figure out, okay, how do we benchmark the specific pieces of the architecture to try to get the best performance out of each one?
It's a tough nut. It's a tough nut. So I've got a slide up. Maybe you can pull it up.
Yep.
The general idea of a micro benchmark is you're going to write a piece of software that is stressing a specific capability in the hardware. And the reason you're doing that is because you want to try to say, ignore everything else for just a second. You know, it's important that the memory works. It's important that the shaders are compiling. But for right now, I just want to know is, do I have good performance for execute indirect? Or do I have good performance for a particular texture read or write, right? And that's what micro benchmarks are all about. So here you can see.
Yeah, you're showing off some here.
Yeah, and I'm starting off. This is XE2 compared to XE3, and I'm showing you effectively the scaling on a per core basis. So if you had roughly the same amount of this is showing Panther Lake versus prior, right? So it's going to take into account configurations and things like that. So
and sorry, when you say prior, you mean Lunar Lake?
Yes, Lunar Lake. Okay. Yes. Yeah. So the way to think about this is there are some things that are not going to change, like the ratios are the same. So that's primarily pixel backend kind of stuff. And so there's small improvements. That 10% there are micro architectural improvements, but the hardware investment to this function has not changed. Okay. Now, if you click forward one, you can say, oh, there's some things that are going up by 1.5x. That's directly related to compute improving by 1.5x, right? So we've increased the amount of area on our compute devices by about 1.5x on Panther Lake versus prior generations. So that comes through in our benchmarks. If this had said to us 1.3, we would know we have a problem. There's something broken in here somewhere because we increased the ratio.
And you know what the theoretical, so when you say you increase the ratio, you mean you put more silicon on that does this math more.
Yes.
So you have an idea of what the theoretical output should be.
And we want you to get 1.5 because we're paying for it.
Yeah.
And if we don't get 1.5, we need to know why.
So there's some bottleneck someplace else that's causing a problem.
And that's what the micro benchmarks are all about. If I gave you a gaming app and said, game run faster, right? You could tell me basically any number. And I wouldn't be able to argue with you because there's all kinds of bottlenecks all over games. But this one, it needs to be 1.5. Right. Okay. And then as you go forward, you start seeing things that are scaling by more than 1.5. So these are things where we've improved the utilization, right? We're to Brad's point, we're fixing things that are where our compute engines were not fully saturated and so this is things like doing better utilization of renames or maybe it's the variable register allocation. There's lots of small things here, and then lastly there's a few things that are dramatically just dramatically faster, and these are things that I don't call it a bug, like it was something that was emulated in software and it didn't work, so we had to do it in software, or it's something that we just missed, but now they're dramatically faster and improves performance overall.
So how do you I assume when you're deciding what's going onto the silicon, you're deciding this at a period of time 3+ years in the past, right?
Yes.
So how do you decide what you're going to do at a time when the games that you're going to be running this hardware aren't even in development yet for the most part?
That's a very good point, Will. And it's you're always trying to engage early with game developers and with game engine developers.
Right.
And there's a bunch of organizations that we collaborate with that are trying to do that forward-looking roadmap. But at the end of the day, it's really up to our architecture team. You know, Murley is our head architect, and he and his team have to be always saying, what do we think is going to be happening with games in 3 years, or what is happening with games and what's happening with compute, what's happening with AI. All of those constraints come together way before you have solid data. So that's what these micro benchmarks are trying to help you with. It's trying to say, can we create a synthetic load that we think is representative of a future gaming load that we don't have yet? And so that's why you start seeing all these desire to tweak it, because we had to make some decisions a long time ago, and sometimes those don't work out perfectly. So we know how to fix it. Why don't we just fix it? Well, the problem is that you got to wait for the next major iteration, because if you make too many variations, you just can't manage that in terms of SoC complexity and also the driver. Yeah.
So the one that had the biggest jump is depth rates. Could you explain what that means for people who might not know?
Yes, so one of the big things that you're trying to do in graphics is not do work that you know you're going to throw away. And one of the best places to do that is with a depth test. So the idea is, if I have a kind of an opaque triangle that is in front of other triangles, and I can figure that out early, then just throw away all those triangles, or throw away all those pixels. Everything behind it.
Yeah.
Right. And so you're trying to do early math that will allow you to punt work. And that's really what this is. This is a new method of triangle elimination early in the pipeline.
That's interesting.
Yeah.
Well, and one of my favorite charts that you've showed before, if you don't mind bringing it up, is the one frame. And you kind of like spell out the individual points of a frame and how things are drawn.
Yeah.
Because, I mean, as somebody who doesn't know a lot about this, it is actually pretty interesting to see this chart.
Actually, before we get into the one frame,
yeah,
I was hoping maybe, Tom, you could talk a little bit more about the increases to L2 and L1 cache, because they're pretty sizable. The L2 cache now matches desktop 580. And the L1 cache is 33% huge. It's colossal.
Yeah.
Like, what are the benefits of that?
The real, I have a little chart that I don't know if we want to pull it up, but it shows the memory traffic that's coming behind the L2. And by increasing the L2, what you're really doing is you're taking pressure off of your external memory system. So with integrated, like Panther Lake, your memory subsystem is one of your most precious resources. So it actually is a better balance to increase the size of the L2 and have a smaller memory interface. So it's sort of like I can make the memory interface bigger and the L2 smaller, but that is a very, very expensive thing to do. And so this is always that tension. You want performance to go up, and you've got only a couple levers on memory traffic. You can make your caches bigger. You can maybe do a little better job of prefetching, but your memory interface is usually one of the most sort of precious resources. So that's what happens. And I do show the rough percentages of decrease of memory traffic. Maybe I'll pull that up real quick. Let me show you that. Of course, it's on my other deck.
I thought that might have been included on that one frame slide, so I wanted to get that question before you explain it.
Yeah. This is the slide I want to show you real quick. So let's pull this guy up. This is showing, I hope, this is the traffic reduction on our SoC fabric with the 16 megabyte L2 cache. And you can see it varies depending on the game and the load, but it's between 17 and 36%. So the point is, this particular investment in real estate takes a lot of pressure off of the memory interface, and that precious resource is better utilized.
So taking the CPU memory burden down increases the amount of memory available for GPU.
Yes.
And then how does the new kind of emerging DDR5 technology impact that too?
Same idea. It's more bandwidth and the same number of pins.
Okay.
So you're basically saying, pins are very expensive. You need huge PHYs and effectively wide number of pins. You may even be pushed into a different package. So minimizing the number of pins is a critical part of product design.
Okay. We have a follow-up question on this. Intuitive Player in the chat asks, so Panther Lake has less memory bandwidth than Lunar Lake, and the cache makes up for it? Is that what you're saying?
I don't think that's the case. I think And Damian, maybe you can pop me a note here about what the total bandwidth was on Lunar Lake versus Panther Lake. But I think it's more opening up more bandwidth than we used to. Right. So by increasing the total number of, like improving the utilization of the memory interface and not decreasing it results in higher performance. Right. We have more bandwidth than we did before.
It's kind of mimicking what they do with the consoles these days, right?
Yeah.
Where it's a shared memory architecture.
Yeah. Similar, right? Well, it is the shared memory architecture, right? The integrated stuff. So here we go. Panther Lake supports LPR5 96. Oh, just went away. Hold on. Stand by. Let me grab it here. So let me see what
it's kind of live fact checking with the whole team behind you. Is really great.
Modern technology. Okay, thank you, Damian. This was disclosed. Panther Lake supports LP5X 9600 versus 8533 on Lunar Lake. So faster memory frequency, same number of pins,
and same
higher bandwidth.
width.
Yeah, and we also have better caching. So think of it as lots more delivered memory bandwidth.
Okay, and
then good job, Damian.
So how does this translate into a frame being rendered?
Okay, so we're gonna go back to the frame
segue.
Okay, drop me down for a second. I'm gonna swap decks here.
Gotcha. Because I mean, it to me, it is always crazy to think that if you're rendering a game at over 120 frames per second, you're talking about doing this.
It's like 8 milliseconds.
Yeah,
every 8 milliseconds this happens.
Yes. Okay,
crazy.
you can pull it up again. Thank you. Okay,
yeah,
so
while you're going through this, Tom,
Yeah.
I think it'd be great if you could kind of explain the benefit from the different registers and variable register.
Sure, I'll try to do that.
That's important.
It's a cool technology. So let's start here, just describing what you're looking at. I think this is a great chart, but it is confusing. So the blue line represents Lunar Lake, so XE2, and the purple line represents Panther Lake, which is XE3, right? And at the end of Panther Lake, and at the end of the day, you want the vertical axis to be shorter. That's faster. So time is on the vertical axis, number of calls is on the horizontal axis. So if you think about it, this game gets compiled and every frame is a series of API calls. And the calls do things like, hey, go load a texture or go compile a shader, or here's some triangles, or here's some, here's some geometry. And then the last call might say render to a surface. Right. So when you render to a surface, it kicks off a whole bunch of activity inside the GPU and it writes some memory. And you may do that 4 or 5 or 6 times for every frame. One call might be doing reflection. Another call might be doing shadows. Another call might be doing a depth pass. And it's a very complicated series of calls. Okay. But every GPU wants to execute the same calls, right? Because the calls result in a picture. And so it's like that's a frame. A frame is executing API calls that is like an artist drawing a picture.
Okay.
Good so far?
Yeah, that's a good way to describe it. I like that.
And now we can compare on a per call basis our XE2 architecture and our XE3 architecture.
And this is all theoretical?
This is real.
This is real. Okay.
Yeah. Okay, so in the beginning, you'll see that purple is faster than blue. And that's because it's bigger, right? So purple is actually running with higher memory bandwidth, which is Panther Lake, higher memory bandwidth, and a wider configuration. This is our 12xe core configuration, so it's about 1.5x wider than our biggest Lunar Lake configuration.
Okay.
So you would expect that the general curve there to be about 50% better if we were getting the full benefit of our larger configuration. That's why on a per call basis it stays lower.
And is this like during vertex setup and stuff like that for the frame? Like what's happening at this point in the
at this point we're doing effectively setup. I don't have the calls written down here, but it's usually I think this is F1, and so it's doing multiple render passes.
Okay.
I'm sorry. This is Cyberpunk. Thanks, Tom. I've got a real-time
really
fact
do, yeah.
checker. So anyway, Cyberpunk's a very, very complicated game render process, and it does deferred rendering and all that kind of stuff. So I'm not certain what's happening here, but it's probably the first pass of generating the G buffer.
Okay.
Yeah, and so you're doing basic. Think of it as like a dumb passive shading where you're getting lots of precursor surfaces that you're going to combine later, and so during this time we're getting a benefit of about 2.93 milliseconds milliseconds from a technology we call variable register and multiple threads. So when you're trying to execute these programs, execute these API calls, they get mapped to threads and registers. And threads are, think of it as a parallel execution through a multi-threaded core, and it gets complicated, but more threads means more parallelism, and registers are sort of the target and the source of the mathematics. So having more registers.
So it's like place data stored and the thing working on the data.
Exactly.
Okay.
And you want more of these threads to be working in parallel. But the key thing is all of these threads execute effectively the same instructions in parallel. And what we can do now is we can have allocations of registers more finely than we used to in the past, and effectively we get better utilization of our register file set, which is one of the most critical resources. If we end up having a program that uses more registers than we physically have, we have to do swapping, and that's like you got to drain the pipeline, you got to like reassign registers. So there's almost just like when you run out of memory, if you run out of registers, bad things happen.
Okay.
So this is showing you 10 threads and more registers, and it saves you 2.93 milliseconds. Okay. Next thing, in this part right here, you see a little bump there. That's the bigger L2 cache is making a difference. So you'll see effectively 0.39 milliseconds saved from a bigger L2. As you go forward,
Is that because of paging stuff in and out, or is that...
this is just like a texture load.
Okay.
If you're doing a texture load, you'll see you're going to become in that moment bandwidth limited, and so having more bandwidth or having sort of effectively more effective use of the bandwidth is important right there. Okay, and then you get back to this variable register thing. Again, having more registers available is very important. We're saving 1.63 milliseconds. Variable register allocation in the L1 cache. Again, this is the idea that memory bandwidth is a huge performance limiter for most integrated graphics designs, and this is showing compute and pixel shaders just pounding on the memory interface. And then lastly, you see having no more spills with variable register allocation. A spill is we figured out that the program is using too many registers, and effectively we're going to have to swap some out and reassign them and drain the pipe. It's very bad, and that's what got fixed on the Xe2 architecture. So that's a walk through a frame.
And and then that happens many times a second.
Yeah, well, that every 60 times, 100 times, 200 times a second. All of this mathematics is replicated on every frame.
That's crazy. So, I mean, one of the things I have from a layman's perspective is that sometimes you hear like, oh, this game really prefers XYZ vendor. Maybe it just runs better on NVIDIA GPUs than on Intel GPUs.
Have you heard of shaders of doom?
No, Have you heard of this?
No. Shaders of doom.
What is this?
Well, different vendor. There's a lot of creative freedom for game designers to code up these things called shaders. And shaders are programs that describe how to color a pixel in general. They also describe geometry, but they mostly describe how to color a pixel. So there's lots of different ways to figure out the color of a pixel based on the lights in the scene, or based on the textures that are loaded, or based on, it gets so complicated. These programs are enormous, but think of it as a program for one pixel. And then we're going to execute that program however many pixels we have.
Okay. Or on the pixels that are affected, right?
Or on the pixels that are affected. Yeah, you can bind shaders to particular locations. It's a very cool idea. It's like I want to write a program that's going to describe one thing, and it's going to describe the color of a pixel. And it's going to use all of the geometric information that's available in the scene to make that decision, but it's going to run in parallel for all pixels or all pixels that are touched. Yeah.
Wow.
So like you'd use them for like reflections before we started doing ray tracing.
Yeah, there could be a different shader for doing reflections, or there could be or just think about direct lighting. If you're direct lighting is the way things used to work. You'd have described lights in a scene, and then for a particular pixel, all you need to know is what color is the material of the thing, what color are the lights in the scene, and what is the angle of the light hitting the surface. Right, and then you can calculate what should that final color be. So this is just how graphics works. So shaders of doom are people are aware of microarchitectural differences across vendors. So sometimes you can do the same thing 6 different ways, and if you happen to know that one way is good for one vendor and one way is bad for another vendor, that sometimes happens. Sometimes you would optimize for the most optimal thing that you care about, and sometimes that means less good for the other guys.
Is this why NVIDIA is like all the graphics acceleration lighting workflows are CUDA optimized for the Unreal Engine and stuff like that?
There is a bit of a kind of an network effect that happens when you get enough installed base and you're deployed widely in the development infrastructure. People tend to optimize on what they have first.
Yeah.
And so that's what you'll see.
Is this stuff you worked on when you were at NVIDIA?
I worked on a lot of things at NVIDIA.
Okay. So you have yourself to thank for having to, no, I don't think overcome some of this?
No, I don't think NVIDIA is doing anything nefarious. I think it's just the leader advantage, right? It's just life.
It's literally 70% of the market is NVIDIA, so you optimize, you run your hardware on NVIDIA because that's what people are going to.
Now our problem is our challenge. I'm not asking NVIDIA to do anything. I'm not asking vendors to do anything, or we're not. We have to work in that environment. We have to work in that environment and that's on us. So we develop technologies that allows us to move past these things that are bad for us. And that means sometimes we'll swap out shaders. So we have teams that are optimizing game performance, and sometimes they'll come across something that we cannot fix in a driver. We just can't do it.
Just because of microarchitecture.
Yeah. Our microarchitecture is not optimized for the way that shader is coded. And so the answer is we'll do our own version of that shader. Right. And then under the covers, dynamically, that shader will get swapped out and it delivers the same pixels. It just does it in a way that's less painful for our hardware.
But just to be clear, having been on the other side of this table before, when you say, hey, NVIDIA, we're having a problem on our 1070s or whatever that we're testing with, and you send the code to them and they run a profiling pass on it, they don't send you a bunch of rewritten shaders that are like shaders of doom. They're just like, hey, you have too many draw calls in this scene and you're using something that's performing weirdly on this architecture and whatever. They're not giving solutions. They're just saying, hey, here's what we saw. Here's
what we saw. And same with us. When we're optimizing a game, we have performance optimizing engineers, and they're looking at the sequence of instructions and what's going wrong in our architecture. Yeah. And then what can we do to fix it? Sometimes it requires a game developer to do something. Sometimes it's our driver that will do something. And sometimes the game is old and the game developer is not around to fix it. So if that's the case and we care about that game enough, we will do the fix ourselves to the degree that we can in a shader.
And I often see people talking about NVIDIA like injecting bad code or whatever, and it's just not, at least at the indie scale I work at, it's not the case.
I've heard lots of things like that, and I don't think any of it's true. Yeah. And I would know. I mean, I really would know. I don't think any of it's true.
Yeah. Okay. Well, you touched on ray tracing a little bit because, shaders for lighting is a way of the past. Now we can do this in real time ray tracing.
Ray tracing's cool.
You talked a lot about ray tracing uplift.
Yes.
And like
Panther Lake.
Yeah, Panther Lake really does have an uplift in ray tracing workloads.
Yes.
Don't you know people don't like ray tracing?
I do. Well, I don't know.
Then why are you focusing so much on it?
It's here's what I think. When ray tracing first came out, it was very inefficient and very expensive because you were running originally on the Battlefield 5 demo that came out when the original ray tracing stuff launched. They ray traced every pixel, so you happen to know that you don't need to ray trace every pixel, especially for reflections, because if it's not reflective, don't run ray tracing there, right? So there's just these things like ray tracing is a new technology. In a very soon patch, as far as I can tell, they only did ray tracing for reflections on things that were reflective. So think about how quickly this technology is kind of being adapted and becoming more critical to future graphics. But we're at the earliest days of ray tracing, and it's still not very efficient, and the algorithms are still developing and evolving. But it's kind of one of these things that Intel, as a large IHV, a large hardware vendor, we have to build the infrastructure, and it has to become ubiquitous before software vendors are going to say, I can rely on this hardware capacity. Because if you're a software vendor right now, you don't have hundreds of millions of PCs with good ray tracing in it. And so you're not going to spend time developing optimizations for integrated ray tracers, right? But over the years, as ray tracing is everywhere, then that infrastructure is there and the software will evolve and people start focusing on it. So that's kind of where we're at. The idea that ray tracing is expensive is very true today, but it's going to get cheaper as software gets better, and having the platform in the hundreds of millions of devices, which is what we do, is going to enable that evolution. Same, by the way, for MPUs. Same, by the way, we have to build.
We'll get to look.
We have to build MPUs for years. for years, and they sit dormant for and this is like any time Intel does anything big like this, it sits dormant. It's just it breaks my heart.
Those MMX2 instructions just now finally getting used is what I'm hearing.
It breaks my heart. Yeah.
Tom, to the ray tracing thing, like the last time we saw a transition that changed the way like kind of games render was like 20 years ago, 25 years ago when we moved from 2D to 3D, really. And there've been incremental enhancements since then, but like that was the last big shift in the same way. And I'm curious, like, you know, whether you're talking about Doom to Quake to Doom 2016 or SNES to N64 to Xbox 360, where are we on that traditional raster lighting pipeline to ray tracing pipeline now? Like, what's the analog?
Oh, yeah. Well, I would say ray tracing is important, but it's not as big as neural rendering. Okay, so in terms of what's changing, the next big step in graphics, AI is going to become the primary method of rendering for graphics. I mean, that's just for sure. And so now the question is, how do we deal with it? How do people evaluate it? How do you think about it?
How do you make it deterministic?
How do you make it deterministic, or do you need it to be deterministic? Like I keep saying, I don't know how we're going to review these things. I don't know. I really don't, because the frames that are being generated are not controlled by a human. And since they're not controlled by a human, there's no artistic intent, right? There's no, what was this frame supposed to be?
You're not selling this great, Tom, right now.
Well, no, I'm just saying it's a problem. I mean, we have to talk about it because it's going to come. It's not like it's not happening. It's merely it's a really big problem. And I think that the reviewers that figure this out are going to be famous.
Well, but at the same time, I don't know, like, as somebody who makes games for a living, I don't know how you like, if you're saying, hey, this doesn't have artistic intent, if this doesn't have authorial intent, how are we making a game that lives inside this neural rendering construct?
Yeah. So I should clarify. I didn't mean there's no artistic intent. Okay. There's definitely artistic intent to the series of frames that are generated. There's all the stuff that game developers do today, they're still going to do, right? There's an author, there's game mechanics, there's game interactions. That's not going away anytime soon. What is going away is pixel accurate rendering intent. Right. So if you think about it today, when you're a game developer, you actually control every color of every pixel is deterministic. Right.
Well, outside of the AA and all the kind of
there's a little, but even that is still deterministic, right? Yeah. And so you can actually capture a reference frame and say this is correct, and you can compare it to future frames and say if there's any pixels that are any different, then there's a bug somewhere, right? Because the process of generating that frame is completely deterministic. That idea is probably limited in its lifetime because you can actually allow AI to generate, let's call it impression equivalent frames, much faster. And I can show you some charts about how come it works. It's just that the processing of a neural engine to generate a frame is much, much faster than the traditional raster pipeline. Okay, and it's not faster by like 30%. It's a lot faster. So that means your trade-off is now I can get much better experiences, but they're not deterministic.
Well, and are you feeding in previous frames into those models to
today,
get out?
Today you are.
Today you are. Okay.
Yeah, but what I keep saying is today is a step along a journey. And the step that we're on right now is the rasterizer generates some frames, and then those rasterized frames go into some AI thing that improves them. Maybe it upscales it, maybe it improves color, maybe it improves contrast. And then that thing is now a new frame. You can do with it whatever you want. Sometimes you can cycle that back into other AI, and now you get 2 frames away from the original rastered, and then 3 frames and 4 frames. And so for me, the real thing that we haven't done yet is figured out what's the right connection between neural renderer engines and graphic intent.
Yeah.
And do you need a rasterizer? Because if you can kind of get the intent without a rastered image, then you can save a lot of work.
Because the thing I've never seen to this point is, hey, we have a game that's actually has some sort of repeatable mechanic that is engaging for people, and then it's rendering that scene with a neural renderer.
Yeah.
That doesn't exist right now.
It doesn't today, but I'm telling you, it's not.
You think it's on the way?
It's not far away.
I remain a little skeptical.
Yeah, I think that for now, my gut says there's going to be a rasterizer around for a long time, because that's really the only way we know right now to capture artistic intent through a game engine and then draw a picture. That's like where we are today. But we're already modifying that image, and we're already super sampling it, and we're already generating subsequent frames and all the rest of it. It's all going to continue to happen. And so what's the next logical evolution? It's maybe how often do you need to raster? Do you need to raster one every 5 or one every 10 or one every 50? It gets hard.
Yeah, Scooby-Doo it.
Yeah, and then the question is, what are the techniques that are going to make that possible? Because I believe this is the problem that people are working on, or that I hope people are working on, is to basically say, and I'll show you that chart, the work to generate a frame using a rasterizer, which is all the shaders and all the compilers and all that kind of stuff.
Let's get to it. Yeah,
Okay.
It's a really good chart. I mean,
All right.
there's a lot to dig into here, and I know a lot of people are probably clutching their pearls, being like, no.
You guys got to fight the chat wars for me.
Back
okay?
in the day, it was the fresh farm to table pixels. You know the exact pixels you were getting.
Yes.
You bought a GPU so that it could make more pixels, and that was the.
Those were the good old days.
It's an easy equation.
Those
right?
were the good old days.
Bigger bar better. Yeah.
I agree. And that we need that kind of quantifiable, repeatable, accurate characterization of generated frames, right? And right now we don't have it.
Yeah. Which I want to get to in a later discussion too. But let's.
All right. So I pulled up a slide here. It's called XeSS2. We launched this earlier with Lunar Lake, and it uses basically 2 different AI techniques. One is called super sampling and the other one is called frame generation to improve performance. So the way it works is pretty simple. This chart, if I get to it, is 1 frame, just like that other picture, only this is time going horizontally, and vertical is floating point and fixed point compute, and the bottom is showing you activity in our geometry pipeline. So this is like everything that's happening on a GPU for this 1 frame, and it's a combination of like mathematics on the top, running compute shaders, and on the bottom it's the like doing triangle things.
And this is an unlabeled axis, but I assume it's like 20 milliseconds probably.
The horizontal axis?
The horizontal axis?
Yeah, I think it's a little quicker than that.
Okay.
Yeah, but I'm not sure.
And do we know which game this is?
Damian, I think this is F1, right? You can chat me on that one. I'm pretty sure this is F1. Okay. All right, so what we also did was labeled the phases, because this is a multi-pass renderer, and on the top, it's a little hard to see in this picture, but you can kind of say, okay, we did the G buffer generation up front, and then we did, yes, this is F1, and then we did a bunch of ray tracing in the middle, and you can see some reflections and some fog and stuff, and then we're doing the back end, and we're doing blending and effectually some AA stuff. This is the rasterization of a frame, and it's just the normal life cycle. I'm sorry you can't see it very well.
No, it's okay. It's my eyes, not your slide.
So when we kind of evolved, we added the capability to do XeSS super res. Okay, so now in this idea, you can see how these pictures look somewhat similar, but the blue sections are shorter. Like this first half is much shorter. It's about half the total duration of the top line. And the reason that's happening is because we're rendering a smaller image. Okay, so now we're not doing that full resolution image. We're doing something that's maybe 75%. So the pixel shading gets much shorter, but that purple stuff gets added. And that is the AI network kicking on using our XMX blocks.
And this is mostly just reduced memory bandwidth for fill rate stuff across the pipeline, or is this compute and everything too?
No, everything
across the board.
Yeah,
okay.
when you render a smaller image, you just get across the board less compute.
Yeah, so it's a 1-to-1 of like, hey, we're rendering less frames so we can do it, less pixels so we can
all the
do it
pixel
faster.
shading happens in parallel basically. So if you have fewer pixels to shade, you get much quicker shading. But the point is that we can generate an image that's not identical to what we did up front. It's actually not at all identical. You can look at lots of pixel differences between the top and the bottom, but our argument is that it's pretty darn close, and you will need to be pretty close to an expert to tell the difference, and you would not be able to tell which is which.
Well, this is one of those situations where you're looking at 100 frames a second, 60 frames a second, and a lot of the differences get lost in the blur of your display.
And it's the truth is that we're dealing with a visual system, and so we are optimizing for the visual system. Right, and you
mean the human visual system?
Yeah, the human visual system, and that's where I think a little bit of this gets wrapped up, because you have 2 choices. You can either have me optimize for the human visual system or not, and if I don't, you get slower performance. And if I do, you get higher performance, but there are imperceptible differences. At least that's our story.
Well, also, but the human visual system is a spectrum of human capability.
Yes,
where
yes.
at one end there's top level esports players who can detect 230 versus 240 frames a second.
Yep.
And at the other end there's Adam.
Yeah, who's like
And me.
smooth 30,
and me.
smooth
Yeah, baby.
40, smooth 40.
All right. So AI came along and it improved the performance by super resolution. Next step was, hey, with XCS2 we did frame gen. Okay, now you can see that little tiny blob is actually all of the work to generate the second frame.
So you're generating 2 frames.
Well, we have the first frame.
Oh, this is a BOGO.
This is the first frame is here, right? The purple.
Buy one, get one.
Yeah.
Buy one, get one.
So you basically in like 2 milliseconds can generate a frame, whereas before we were talking up top here like 20 milliseconds, right? So it's just dramatically faster. Now there are differences. But our job is to make it so that you, in general, would prefer the 2-to-1 versus the 1, right?
Yeah, because what we're not showing here is what it looks like.
Yeah, you're not.
And I think that's, I mean, I think there's different camps. Some people can see it, and when it falls apart, it is noticeable.
Yeah,
It's like,
totally.
Okay, yeah.
And that's I'll get to it on the next slide, but I'll tell you how I think about it, and it is a very good point. And that's why I say these frames are not the same. Like, it's not fair to say my frame rate is 2x. And I don't do that. I don't claim that this is a 2x.
Some people do that.
I know, but I don't.
Some people say that the one generation budget card is going to be as performant as the last generation high-end card.
I think it's just easier to be more transparent than
Okay.
that, right? And the way I can be transparent is to tell you there are 2 types of frames. There is the first frame, which was rastered. It's your comfy old frame that you've known
Farm
forever.
to table pixels is what we call
Exactly. And then there's these other things. Now the other things are, I call them visual improvement frames. Right, they are there. They're like salt and pepper.
Oh, VIFs.
Yeah,
VIFs.
VIFs.
Oh, no.
They're the salt and pepper. They're a little butter. They're a little sauce.
Yes.
Yeah, a little sprinkle.
Okay. Now you can either have sauce or no sauce.
Yeah.
It's not like it's you don't have to have them, but you can.
As of right now, you don't have to have them.
As of right now, you don't have to have them. Okay. Then, I'm sorry. Did I? So I jump right into the smoothness topic after this, and then I'll show you the multi-frame stuff.
Okay.
All right. So what I was just talking about is
Actually, let's hold this.
Okay.
'Cause, I want to have a deeper conversation here.
Okay.
Yeah.
So you want to go about multi-frame then?
Yeah. Let's do
Okay.
multi-frame.
All right,
Yeah.
so
let's add on top of that.
Hold on. Let me come down for a second, and I'm going to go multi-frame. All right.
Because this is what's new.
Yeah.
Part of Panther Lake. Part of XE3.
Yep.
Is introducing multi-frame generation.
Yes,
You had 2 times. Now you can have up to 4 times.
Multiple, yeah.
Yeah.
So this, you can come back up. This picture is showing you what we just talked about, only I broke it down a little bit. So if you remember, there was super resolution that happened, and then there was frame gen. Now, if you look at that frame gen, it says there's 2 things happening. The first thing is optical flow. And that's an AI network that is looking at pixels from one frame to another, calculating the relative motion of those pixels. It's a kind of a neat idea. If I knew the direction and magnitude of motion of every pixel, then I don't need to re-render. I'll just move the pixels.
Yeah.
Right. And that represents motion. By the way, that's how movies work. Right. MPEG is a motion vector based encoding of pixels. Right. So with multi-frame generation, we do this. We take the same optical flow and we don't generate 1, we do 1, 2, 3 more, right? So it's
up to 4.
Up to 4 right now. And what's cool about that is, again, the 4 doing this generation is actually so much faster. Now, the only question is, are they good? Are they good enough? And that's where I think people get hung up, right? We're still, some people say, I don't like it. I'm like, you know what? Some people don't like smooth motion on TVs. And that's why there are that's why there are settings on there, right? And that's everybody does their thing. This is an option; it's not required.
So are you getting the optical flow vectors? You're taking those by looking at the rendered frames, not taking vectors from the game itself.
Right.
Okay.
Right. There are both done here. Optical flow is generally looking at pixels, not looking at motion vectors from the game. Game motion vectors are normally object motion vectors.
Okay.
So they're talking about like a ball moving or a character moving or a joint moving. These are, I'm looking at one frame to the next and comparing the pixels.
I mean, basically.
We are, in fact, the algorithm does take both.
Okay.
Yeah.
Okay.
All right, so what I think is your point, and I think a lot of gamers have the same concern, is these are not the same, Right? These frames that we're talking about are not the same, and that's why we don't pretend that they are the same. As a matter of fact, I've got a team that works with me doing something called PresentMon, and PresentMon is the largest deployed tool. Everybody uses it for performance.
We love PresentMon,
everybody uses it, and we keep developing it. It's open source. It's on GitHub. Go check it out. And we make a tool that wraps up PresentMon and provides a user interface. Okay, and so let me show you what that looks like real quick. I'm going to take it down. The reason I like to show it is because it highlights how can we navigate through this chaos right now, right? And at the end of the day, it's all about transparency for me. You have to be able to say, I have a native engine that will render at some rate, and then I have AI technologies that are different. And conflagrating those together, I think, confuses people rather than clarifies. And I hate to normally add complexity to this, but in the case of AI, there is some complexity.
Well, and I think the other thing too is that people are upset because they feel like a lot of developers are leaning on these technologies. Yes, you still have the choice, but the problem is that the old choice is now becoming less and less performant for your hardware, and there are some games that literally have that choice on by default.
Yes.
And like Will always says, defaults matter.
Yeah.
Defaults matter more than anything else.
Yeah, because most people never open a control panel.
Most people are never going to open the settings pane.
Yeah. So this is what I call a smoothness metric. Okay, and that's primarily what AI is doing today. When you talk about frame generation, it's making your experience smoother. And it's not just by blurring everything and making it muddy. It's actually literally smoother, and it depends on your game, and it depends on your visual subsystem for yourself. But when I think about it, it's primarily a smoothing technology. That's why in PresentMon we've added 3 different versions of frames per second. So everybody's used to FPS is the thing I look at for performance. Well, now in PresentMon you've got 3 different numbers. There's FPS app, there's FPS display, and FPS presents. And those are 3 numbers because they're different ways of looking at performance. So app is what is the application think frame rate is. So that's what you would think are rastered frames.
Yeah, that's how many times it's going through that traditional pipeline.
Physics.
These are the farm-to-table real
These
frames.
are farm-to-table real frames. But interestingly, they're not necessarily the frames that you see. Because even before AI, there were things like drop frames happening and windowed mode. You could have a game that thought it was rendering at 90 frames a second, but you're only seeing 30. Or you're only seeing 45 because of the Windows subsystem and graphics and windowing and all that stuff. So frames per second app is not the same as frame per second display. Frame per second display is how many frames are shown on your screen. Right, and that includes things like drop frames. It includes things like variable refresh rate. It includes things like frame pacing. So if you're a hardware vendor that has pacing on the backside, like you're pacing the rate at which you display a frame, the rate that this is showing, it's showing you the frame time correctly. So I'm showing you averages here, but all of these are actually frame times, and
you're just computing an average.
Yeah,
based on
but
the frame time.
you can do whatever you want. We show the frames, we show the rolling averages, lots of stuff. So the reason that's important is because NVIDIA does do frame pacing on display. Mm-hmm. So when they do frame gen, their frames per second presents is going to be very clustered where the AI runs. But those frames are not as bad as you think. If you look at the 1% for FPS presented, they're going to suck, right? But if you look at the 1% for FPS displayed, they're beautiful. Because there's pacing on the backside, not on the front side.
Because the thing that it turns out we detect as humans isn't changes in average frame rate. What we detect is large variances in a cluster of frames in terms of like frame timing. So if one frame is 8.6 milliseconds, the next one's 12, and the one after that is 9, and the next one's 13, and the next one's back to 8. That feels like a stutter for us.
It does. And that's why there's lots of different ways to look at this. And we've decided we're just going to make it all transparent. So now, as a gamer, you can look at FPS average and say, that's kind of like my farm-to-table frame.
Do you cut out things like menu loads? Like, say I'm playing Battlefield and I die and the menu load happens, that always spikes the frame time while the menu load hits.
We don't change it. We don't know any of that stuff. Yeah. Okay. The last one is FPS presents. Now, FPS presents is the amount of frames submitted to the render pipeline. So think of it as the game can submit frames, but also AI can submit frames. Okay, so think of it as this is all your frames. And normally FPS displayed will be the same as FPS presents, but sometimes it'll be less. The pattern of FPS presents is very different than the pattern of FPS displayed.
Why show both then?
Because we want to be fair. And if I had my way, I wouldn't show you displayed.
Oh, really?
Yeah, because I don't have pacing on my yeah.
Oh,
Yet, but we do. I mean, obviously we do have pacing, but it's not as old as that one. So people want to know, like, how smooth is my experience, and sometimes that means FPS displayed using the flip metering.
That's the eyes. Eyes measure.
That's the frames that you're seeing. Yeah. Now, none of this, by the way, is considering what is the animation that's encoded in the frame. So the other side, this is all talking about frames that show up on the screen. There's another part, which is what is the animation that's being encoded into each frame, right? And they both have to be in sync.
Yeah, so I think here's a good part to ask this question from friend of the show, mostly running at Stockish. Said for Tom, can you help everyone understand Gamers Nexus's animation error methodology white paper? I am also going to ask you, please help us describe that, because I said this is what you're talking about.
Yeah,
right?
This is what this is about. So I added we added a new metric called animation error. It's in Presentmon today, and everybody can try it out. It is available online, all the sources there. It's a very simple calculation. It says the rate that animation is moving forward in the physics engine, like how if it might be going one step for a ball in one frame and another step for a ball in another frame. There's an applied time to all of that because motion is consistent, and so now every frame has a picture that has some time associated with it.
And that's divorced from what's being displayed.
Exactly.
On your display.
I was going to say, the physics engine is usually locked at a certain tick rate for very good reasons.
Oh, yeah, absolutely. And those tick rates, that step is encoded into the motion in the image, right? So if you got a ball moving across the screen, the position really kind of represents time because the velocity is stable. So you need to show those pictures. Each picture is separated by time, right? And so if you don't match that separation when you show those frames, people feel stutter. And that's actually what stutter is. Stutter is not this percentile stuff. Stutter is fast acceleration caused by either animation being in the wrong spot displayed evenly, or animation being in the wrong spot, animation being in the right spot but displayed unevenly, right? So it can come both ways, and they're both identical.
Perceptually.
Yeah, perceptually identical. Yeah,
well,
you can go ahead.
Yeah, well, I was going to say, like, for me, who's, once again, thank you for helping to explain all this stuff to a noob like myself. But as somebody who has a background in film, I was thinking like, the frame rate is different than the FPS, like, that it's encoded in. So it's like, you could shoot something, at a higher frame rate for like an action shot, but it's still displayed at 24 frames a second.
And it's very confusing. Same idea.
Yeah, so it's like, what's happening in there is different than what's actually
shutter speed. You mean
shutter speed. I'm sorry. Yeah.
Now,
Shutter speed versus frame rate.
I will say that this whole issue about animation error and FPS are just measuring two different things. FPS is measuring sort of your brain's ability to generate a interpolated, smooth experience, right? And the more often you show frames, the less work your brain has to do trying to figure out what motion is, right? And that's you can say that's more like a shuttery kind of a shutter. Or you can when you slow down movies enough, you can see that it's individual pictures. And as you get faster and faster and faster, you can't anymore because your brain kind of creates this. Oh, I'm looking at real life. It's not pictures. It's motion. The other thing that our brain is very good at is realizing acceleration, and it's shockingly good at that. And acceleration is anytime you see something jerk, even if you're not looking at it, you still perceive it. Right. So imagine that there's a whole field of pixels that jerk at the same time. Right. Your brain sees that beautifully. Now, if you show the same amount of motion smoothly without any jerkiness, you don't see anything. You just think it's real life. So this is your brain being tuned to acceleration, and we think it all goes back to, I told Steve, it's monkey brains, right? It's all about when you're evolving. One of the first things you do is learn how to not get eaten. And that relies on acceleration recognition.
Oh, how fast is something coming towards me? Do I need to worry?
Yeah, do I need to jump? Yeah. and so your whole fight or flight reflex, that is what we're talking about with stutter.
So then we talked about visual perception. Well, what about motion perception? When you're generating these frames, and I find typically with a gamepad, I don't notice the generated frames as much because the motion is a little bit more interpolated, a little bit less one-to-one than it is when I'm using a mouse and keyboard for input.
Yeah.
NVIDIA, obviously with the 5 series, did a whole bunch of work to like take your mouse vectors and shift the frames and then render in the gaps that weren't being rendered naturally and all that. And it actually made a big noticeable difference in how mouse and keyboard worked with generated frames.
Yeah.
And I'm curious like where the XE stuff is with that at this point.
Oh, it's latency related to frame generation is an important problem to fix, and we have a bunch of different technologies that I think are going to make a sizable impact on that. We're not using the same approach that NVIDIA is using. I don't really like the fill idea, although there might be some fill that's required. You can actually do better things.
Okay.
Yeah, but latency reduction for frame gen specifically is super important.
Input for
movement to pixel. I want to separate the latency that we talk about. A lot of times we talk about click to photon latency, which cannot really be fixed, right? Click to photon goes up to the cloud. It does some simulation, or maybe it's locally, but you're talking about motion that takes hundreds of milliseconds. So when you click, you don't see a muzzle right away. It's got to go into a game engine. The game engine has to figure out, do I have bullets? What animation steps do I want? You don't like put an explosion out. You start the gun barely moving, right? And so those effects are hundreds of milliseconds as you imagine seeing a click to photon.
And that could have artistic intent behind it.
It does.
Because maybe if the gun is slow to fire.
A lot of guns have trigger lag, all that stuff.
And if I improve that by, say, 7 or 8 milliseconds, it's done nothing, right? So, but what is feelable is motion. So as you're moving the mouse, you have an expectation that the entire field is going to match that motion, and right away when it's a few milliseconds behind. So fixing
floaty is kind of a
fixing
term.
Like motion to rotation is what actually needs to get fixed.
And you can test that, I find, by like looking at a point on the screen and trying to move your mouse and hit the crosshair right on that spot.
Yeah, it's really hard.
And it's really hard to do
with any lag. Yeah. So that problem there are multiple different solutions for, and it becomes much more predictable.
Okay.
Right. Whereas somebody just happened to click a button. You didn't have any idea that they were going to click a button. There's not much you can do to make that look faster. Motion, you do know, right? You know what they're doing already.
You have vectors from the mouse input.
Yeah. If I'm going like this, odds are I'm going to keep going like this. Right. And it very much becomes more predictable.
SE2 in the chat asked, what's up is there going to be a present mon for Linux at some point?
Oh, yeah.
I don't know the answer to that. I do not expect so, but it's because PresentMon is a hugely complicated thing.
Yeah. And
it primarily looks at ETW events coming from Windows. I guess it could be modified to look at a Linux sort of series of events, but I'm just so much not a Linux guy that I don't even know what the events are in Linux.
Well, you're here with 2 Linux experts.
Yeah.
I don't know
Is there
start the podcast.
We have a podcast.
Is there something equivalent to ETW?
Almost certainly.
I'm sure.
Do you know I know what it is? Absolutely not.
Is it open source?
Yeah,
Probably.
Yeah, probably. So I would say right now there's no plans to do that. But of course, as things change, and if gaming on Linux became more important for us, like for SteamOS or an example like that, we would definitely look at something like that. Okay. And if anybody wants to take our open source repository for PresentMon and go do a Linux version, Godspeed.
Okay.
Oh, so PresentMon is open source.
Yes.
Yeah.
Yes.
Yeah.
And it's permissive.
Okay.
Yeah.
All right. Well, there you go.
And I kind of wish it was a little less permissive, but it's pretty permissive.
Love that MIT license, right?
Some people have taken PresentMon and done crazy things with it. Like, for example, embedded it in their own performance tool and put a thin wrapper around it and not credit us.
Oh, I've heard of these. Yeah. I've heard of these.
Yeah.
Interesting.
Yeah.
Okay.
I don't mind if you do that. I just wish you would credit us. That's all.
Let's just give credit.
Yeah.
Yeah. It's not that hard, right?
Yeah.
Thanks to Intel.
Well, I mean, you GPL license that thing. They have to.
Okay, so you're talking about things to help mitigate this transitional period that we have.
Yes.
Right?
Yes.
And you're also talking about future things.
But not products.
Not products.
I'm
You're
not talking about future products,
but
I can talk abstractly.
yeah. But you're talking about building a better GPU, or building better games.
Building better games.
Also building better ways for us to perceive what's happening in games.
Yes.
I kind of want to. Sorry, I'm getting to something. It takes
you're building.
That was called a transition.
That was
called a transition.
Building up. It's building up.
Yeah.
All right.
So
good job.
And you're talking about technologies that should potentially come in the future, like a potential celestial, whenever it comes.
Your words, not mine.
Yeah. How much does this translate to the whole stack? Because, and this is my first question. You on Panther Lake, you showed off two different configurations: one 4-core, one 12-core for the GPU. Obviously, if there's, I don't know what the Xe3P, how many GPU cores?
I do not know the configuration. I don't know if we've announced Crescent Island.
Okay, but it's bigger than 12.
Bigger.
Okay, way bigger than 12.
Way bigger.
And theoretically, something discrete would be bigger too. I think that's the other hard part for a handheld person like me, right? A lot of people argue, like, if you have a big, dedicated, beefy GPU, then your need for some of these technologies is pretty minimal. But if you have a handheld that is down in a 12-core, 8-core configuration on Lunar Lake or something, you actually need more of this because you're having to overcome just pure grunt.
Yeah, and I would say battery life.
Oh, right, exactly. Right? Yeah. So how much of this technology is being pushed forward because of the low end?
I think it's a great question. AI is dramatically more power efficient at generating frames than traditional raster. Mm-hmm. And so if you are in any kind of mobile environment, I think the trade-off you probably would prefer is some hybrid right now where you do some rastered frames and some generated frames. And that's simply because you're going to get a really good experience at way lower power. Okay. And so anybody who's in mobile will take that. But I do think that you're again kind of hinting at, we are now primarily investing in things that are not traditional raster. Right, and that could be post effects, that could be AI effects, it could be generation effects, it could be replacing the entire pipeline. Like I showed a demo at ITT that was called a Nerf demo. I don't know if you remember that one. It's kind of crazy, and what it did was said, how about we make games dramatically cheaper? And the way to make games dramatically cheaper to develop is to remove a lot of the drudgery of model creation. Okay, so to simplify that, this guy did an experiment. He said, what if we replace the entire pipeline with AI? And the way we're going to do it is we're going to take a model and we're going to take pictures of it. And all we're going to do is take pictures of it, and then I'm going to train an AI so that if I ever shoot a light at a spot, then I can calculate the color of that spot, which is exactly what we talk about with these shaders, right? Shaders calculate the color of a spot. So how about I give an AI model that calculates the color of a spot? And they did it. I showed it live running on Panther Lake, and there's no geometry. There's no shaders. There is no lighting.
There's no movement.
He was doing camera rotation.
Well, the camera was rotating, but the model wasn't.
The model does not
move.
move. Yeah. You need multiple models, or you need a new model that deals with motion. Yeah.
Also, the model didn't look, surprisingly.
No. But again,
well.
you're looking. You're absolutely right. It didn't look great. But it did look. It was you could see what it was.
Is this the teapot? Is this the Stanford teapot? Is that what we're looking at here?
No, it was a Nerf. It was a Nerf.
No, I'm just saying. Is this the
yes.
AI equivalent of that?
I think it is. My point is that, like, when you saw, and I don't want to make too many analogies to like telephones or telegraphs or like anything early, it usually sucks in the first version, and I think this is no different. But when I saw it, it took me a while to understand what am I looking at, and what you're looking at is AI model that has been trained with photographs that can do 3D rotation, you can do lighting, you can do shading, and it's all encompassed into this one very lightweight model.
Because you don't have to have the different shaders for the different angles and lighting and all that. Yeah.
That to me seems like skipping straight to the end.
Yes. You will be lots of other things before that.
Yeah, I was going to say the stuff that I've seen that's really interesting in the AI space is things like accelerating or helping technical artists figure out how to do rigs and skeletons, stuff like that.
Oh, yeah.
Doing fill-in animations or whatever. Much less sexy, much less kind of exciting and fully finished.
But it still dramatically reduces the load on the artist, right?
Yeah.
I think that's true. You'll see AI applied to the current workflows, and it's going to basically make it a lot easier.
Also, Willis missed my my transition. That was well, so the other thing is that, especially in mobile on Panther Lake, we've got one right here.
Nice.
It's
definitely not made of plastic.
Yeah, weird.
Bigger than I thought too.
Yeah.
See that.
So
That's
we're talking about.
Did you put it together right, Tom? That's the question.
It's nice. It's a graphics die right there.
Yeah, there you go. It's limited die space. Oh, the filler tile.
Yeah.
2 filler tiles now.
Crazy,
wow,
right?
double the filler
all that
tiles.
extra space.
I know.
Yeah, well, so
wish I was
that's
so
the thing. You have limited space on these tiles.
Yeah.
More and more of it is getting dedicated to other things like RT cores, NPU. People are like, I don't want an NPU. Why don't you give me a bigger GPU? Like why spend so much space on things that are coming in the future?
I see. That's a tough nut.
You talked about it a little bit before, but yeah.
The way I think about it is, first of all, Panther Lake represents our largest integrated graphics device ever by far. Right?
In terms of millimeters on the square millimeters on the die?
Die cost, relative cost of the CPU to the GPU, this is the biggest we've ever done. With 12 Xe cores, it is effectively destroying the low end of discrete.
I was going to say, because to be clear, like the Battle Mage was 20 Xe cores?
I think so.
Yeah.
Yeah. So this guy, performance-wise, is definitely hitting what most people would have thought of as discrete level of performance. I did have a question, and I don't know, Damian, if we ever answered it. How far back do we have to go to get to a discrete that would do this?
Mm-hmm.
Oh yeah, you did ask that as a question.
Yeah,
we all submitted our
what
answers.
was the answer? Do you know?
I never saw the answer.
I think I don't want to bring it up, but the question I asked, if somebody wants to figure this out, what generation of discrete?
Well, if you count the multi-frame, it's probably like a 3060.
No, I'm not going to count the multi-frame.
Yeah. Pure farm to table pixels.
Yeah. Farm to table pixels.
Yeah, maybe that'll be part of my benchmark suite.
Do it.
Yeah.
How far back? And I'll be embarrassed if it's like more than a 1080. I will.
I mean, 1080 is a goat, though. If you can get a goat.
So this is,
right there.
and again, I don't want to say too much because I actually don't know the answer. Normally, I like to have these stories when I know the answer.
Yeah.
But so I'm curious.
Well, so then the next question I have is, will there be other configurations? There's 2. There's a 4 and a 12.
Yeah.
But in the past generations, you've had 8, so it seems like a really big jump.
Yeah.
There are competitors in the space. AMD Strix Halo has 40.
Yes.
Like what?
The way I think about it is the product stack normally is a eat the whole cow strategy. Right. And that means that when we build dies, we have 2 dies that are the graphics dies. Mm-hmm. They're going to yield perfect die, and that's going to be a SKU, but they're also going to yield dies that don't have all the things working. And so those dies get repurposed in the stack typically, right? They're perfectly fine. There's circuits on board that allow us to disable bad things. And sometimes you do that by choice. Sometimes you do that because you have a defect. So rather than throwing these die away, you repurpose them, right? And so we haven't announced anything about Lunar Lake Stack, but I do know that Lunar Lake is going to be broad.
You mean Panther Lake?
I'm sorry, Panther Lake, yeah. So Panther Lake is going to be broad. It's going to cover most of the segments that we do today with Lunar and Arrow, right? So think of it as this is the very beginning of this product family, and there are very likely going to be multiple SKUs covering multiple different segments.
So, and...
Oh,
go ahead, Brad.
Sorry, I just had a quick question. So you built a T3 around 6 Xe cores each render slice. Is that the reason why the 2 lower end Panther Lake configurations have 4 Xe cores instead of 6? I was just kind of confused as to why that is.
Say it one more time, Brad.
The lower end Panther Lake
4, yeah,
have 4 instead of 6, even though Xe3 is built around 6.
Right. So the way to think about it is that those 4 configurations, those SoCs, tend to land in 2 different places. One is consumer piece, sort of like commercial PCs, where graphics is not the primary workload, but you still need graphics. You need to have good graphics for Windows, but you don't need a lot more than that. That's the 4 configuration native. But you'll also note that die has a bigger PCI Express interface, right? So effectively, that die also mates very well with discrete GPUs. Right, so if you're going to build a high-end gaming platform to compete with like a Halo design or a Strix design, what you would do is you'd take one of the more core-oriented, CPU core-oriented SoCs, and you would bundle that with a discrete GPU. Right, so you got to think about these. These do not live alone; they live in an ecosystem where there's discrete GPUs, and that's probably a better choice from a cost perspective than doing a gigantic 40-core iGPU.
Well, yeah, intuitive player in the chat is asking, are monolith dies gone, or monolith CPUs? Like,
I don't think they're gone. I think it's this we have very, very complex discussions and hard decisions to make about what goes where. And it's all about where's the process, how big's the die, what's the defect density predicted to be, and it's always evaluated, always reevaluated. But the product platform team, that's what they live for. They're looking at package costs, they're looking at die yields, they're looking at everything that makes this a product can be done 10 different ways.
I was just saying on that front, one of the things you talked about at the Tech Tour was that gaming, because of thermal and headroom and stuff like that, often you were talking about running games on E cores instead of P cores because it gives more thermal overhead for the GPU in the same package. And I'm curious if that means we're going to see potentially oops all E core variants of these processors that are for those lighter gaming workloads.
Yeah. Well, I don't want to talk about any undisclosed products or future product plans.
Of course.
Yeah. But the idea that certain workloads would have a preference for certain types of core distributions, I'm sure we look at that all the time.
Okay.
Right now, I don't think the segment question is a harder question because you need a big enough volume to justify building a dedicated SoC, and that is tough nut, right? It's got to be big volume if we're going to build a chip.
It's like not 18
chips. It's not 18 guys. It's not. It's a lot.
I'd buy one.
It's lots.
Well, so I mean, it looks like with this, you're taking a shot at the low end discrete GPUs, right?
Yeah, I think the performance of this, I mean, I don't know if it's a shot at low end discrete and we had this conversation, is the low end what defines low end discrete is constantly changing, right? And so like I view it as these curves that are always going up, and games are always getting, low end gaming is always getting a little better. It's getting a little bit more graphic. It's getting a little bit higher workload. Engines are always getting more complex. So low end discrete, what that is, always pushes up. Now the question is, what's our rate of change compared to low end discrete? Are we getting faster than low end discrete is getting faster? That's another good question for you.
Well, and is there a new baseline established by the Steam Deck and the rise of those kind of low end, like at this point kind of ancient APUs?
Yeah, I view all of this as many people predicted that integration would have overtaken discrete GPUs by now, right? It's just kind of like, how is it possible that we have not already eaten up discrete GPUs? And the reason is, and I think that's what's different about discrete GPUs, is that there's an insatiable appetite for visual quality, right? And that bar moves up as quickly as GPUs get faster.
Well, and the other thing is people wanted a bunch of AI compute on their
AI mucking things up. Well, yeah, because that was my next follow-on. We're talking about building bigger SoCs with chiplet designs. We're talking about more efficiency, all that kind of stuff.
Yeah,
that kind of stuff matters less when somebody's building a high-end desktop, and they don't care. I mean, obviously, I know you're not going to talk about unannounced products for the desktop, but how does that math change when you think about the desktop market, which is going to have usually a discrete GPU? Or do you think there will be desktops in the future where people just don't buy discrete GPUs?
Well, there already are desktops where people don't buy discrete GPUs, right?
Sure.
But so I would say I do think that there's going to be a market for high-end graphics that is not going away anytime soon. And that's going to be probably a desktop, simply because form factor is important, power is important, and you can't get enough power into a mobile form factor to do what you want, really. But it's just kind of hard to know what's the boundary between an integrated design and a discrete design. And it is true that integrated is going to continue to get increasingly competent. And these things, which are these hybrid designs with chiplets, continue to blur that line, right? Because what's integrated? Does it mean that there's like a crack in the die here? Does that make it integrated?
Yeah. Are you talking in the same memory? Like, is the same memory controller feeding the GPU?
Is it a common memory?
And the CPU? Yeah.
If that's the definitive integrated, then that's fine. But there's lots of ways to think about this. And to me, those designs are going to continue to get increasingly competent. And at some point, you're going to be squeezing that market eventually. Maybe someday.
There's a lot of cheddar in that market, I'm guessing.
Yeah, it's a lot of cheddar cheese.
Yeah, okay.
A lot of cheddar cheese. Get in there.
Okay.
Yeah.
Do you have any follow-ups, or should we get to some questions before? Yeah, because we're running low on time. I know.
I can start the questions.
Okay, go for it.
Please.
Bring it, baby. Bring it.
So it's kind of a broad question, actually. Earlier we were talking about how most people never open control panel because they won't. But for XES3, XESS3, FSR3, and DLSS3, like you need to use the overrides to do them for the games that came up from the second gen.
Right.
That's really user unfriendly, I find.
Yes.
Like, is this a necessary evil? Is there a way the industry could be doing this better?
Well, there is, and I think what's missing here is Microsoft has not yet standardized the way post effects work. And that's really what I would love to see happen is some kind of DirectX Next where things that we're doing with AI and things that we're doing with post effects and things that, FSR, DLSS, Reflex, XELL, all of that have very similar APIs. Like they're different APIs, but they're not that bad.
The things they're asking for are the same.
The things
right?
they're asking for are very, very similar. And so what we would want is a way to discover capabilities on the platform. DirectX already has a way to discover capabilities on a platform. We would want a way to standardize APIs. Well, DirectX already standardizes APIs. So what we would really like is that to be the unifying base. And what's missing is discovery. You need a way to know the names of things, to know the menus of things, to know the options of things, and all of that is just uncovered right now.
Well, NVIDIA has a tool for that, but I think people are a little hesitant.
Yeah, well, Streamline.
Integrate that.
I mean, we tried to partner with NVIDIA on Streamline for a long time. Streamline is NVIDIA. We should talk to NVIDIA about it, but my take on Streamline is it's their attempt to do exactly that.
Yeah.
Right? They're trying to create an API for post effects that is open and industry standard because it sucks to be a game developer and have 3 different APIs that you have to integrate that do the same thing.
And it's often the person that, weirdly, the UI person is often the person whose time is most valuable.
Yeah,
at the stage
it's just a terrible solution. Yeah. And so what we really need is a few things that are not in Streamline. So Streamline doesn't have the ability to discover UI, right? So there's no way for an independent hardware vendor to say, "Hey, I am an upscaling of Vect, and I have these options. Please make sure that these names show up in the UI with this structure." That's missing from Streamline, and until that happens, users of Streamline are still in the same spot where you have to go to each individual game developer and do custom integrations of your technology, which is not a winning strategy for anybody. So there's that whole problem has not yet been solved, but it's
typically Microsoft solves this kind of
typically
problem.
Microsoft solves this problem. They just have not yet. They tried with what they call it SR, Direct SR, which is their first attempt at doing super resolution. But you can see already that that's not getting dramatically adopted because there's already been integrations for super res, and now everybody's on to the next thing. Yeah. And that is going to be the problem with doing per effect APIs. We don't want, or I don't think we need per effect APIs. I think we need an effect API. Yeah, and that you would then plug in over time. Another thing that's missing right now is standardized timing APIs. So if you just look at all the stuff I just talked about with animation error, it's requiring the presentmon to know about the time of every frame. And today there's no API that does that. So there's nobody that's telling us the time of every frame. Reflex does it. XELL does it. So when games are designed with those technologies, we know the right frame times. Otherwise, we have to estimate the time.
I was going to say, is measuring those times, is there a performance impact to measuring those times as well? Okay.
It's zero. It's just the game engine has to measure, it has to calculate that time, and there's a simple API call to tell us
tell you the time.
Yeah.
Okay.
Yeah.
And then display it.
Yeah, and all of that can be standardized. So I'm thinking about maybe we should do a presentmon SDK that would basically take all the timestamps that presentmon needs and give it to the game developers or game engine developers and say, just integrate this and I'll take care of everything else. It's a pain in the ass. I wish Microsoft would do it, but we don't have a solution yet.
Okay. I do have a question from one Adam Patrick Murray that I forgot to ask earlier. So we were talking about the animation error stuff. Steve had that good video, trying to look forward to how do we benchmark this stuff. I'm going to ask you, how do you think people should be reviewing these GPs coming in the future?
So you mean, we still need a farm to table frame number. Okay. So let's just say you need to know how big your engine is. That's your farm to table number. Then I think we need a way to characterize smoothness given all the different technologies, right? And so smoothness characterization for me is animation error. And the way animation error works is it calculates, jitter effectively in the animation. And what you ought to do is add it all up for your run and divide it by the length. Basically that will be animation error in milliseconds per second, right? And that gives you a very good measure of how hitchy your things are. Right. And that number would be lower for things that did better jobs of synchronizing animation, synchronizing the animation timing with the display timing. And then, so what you're testing at that point is one GPU's ability versus another GPU's ability to. Yeah. Like you only think about frames per second because over the years, you've been able to affiliate your experience with some random number. Right. And so when you say 60 FPS, you know what that means. That's pretty good. And maybe when 30 FPS, that's pretty, it's not great. It's console-like. Right. Yeah, console-like. And so with smoothness, we just need a chance to start understanding what these numbers mean. And the numbers are not going to be big. It's going to be maybe 2 milliseconds. But if you think about 2 milliseconds of jitter on every frame.
2 milliseconds of jitter on an 8 millisecond frame is a lot of jitter.
It's a lot of jitter, right? So that would be a shitty experience. So it's sort of like, over time, I think we'll figure out what these numbers are. And I do think we have the capacity to put a tool out that would allow people to change these numbers in a slider effectively and then look at it. Okay, because that's the other thing, like gathering the information is one part. Yeah. And then the other part that we struggle with is like, okay, how do we present this in a way that also then the internet doesn't take and just try to argue about on Twitter, right? I feel like what we need is a series of movies where there's known patterns, and imagine that I do a test app that you can slide a distribution of animation error around, and then you can just run it, and you'll get that experience. So a synthetic benchmark. Yeah.
Well, but I think not even a synthetic benchmark. I think you need to give somebody something they can see in controlled circumstance, so they can experience it in a way that says, "Hey, you're about to get some animation error," and then you see what it looks like. Yeah. Because once like I've been doing these videos where I render the frame times on top of the video, and it's really informative because you see things like Battlefield 6 in the single player has this really gorgeous volumetric smoke that they pop up occasionally, and when that hits, that frame time just goes way through the ceiling until the smoke goes away, and then it goes back down. And when you start seeing that stuff, you start associating these things with the things that are causing them. Yeah. But without recording the frame times, overlaying them on a video in Premiere, watching that video back 50 times, and figuring out, this is the commonality across these 10 clips. Yeah. Well, it's really hard to be able to like internalize what's causing these dips.
But that's also testing the game, not the GPU versus GPU. So then how do you say, this GPU is better at that thing that you just showed than my thinking, and this is, I'm really close to doing this, is that we just need an app that is very simple. And I already mentioned to you guys off campus that we have access to game engines. Everybody's got access to game engines. So we can add the features to inject the errors. So we can inject errors in a controllable way. And then what you'd want is some kind of pattern that is predictable to humans. Maybe it's just a bar scrolling back left and right. Maybe it's a ball circling in the air.
Maybe it's a character running back and forth.
Maybe it's a character running back and forth, right? And then maybe I'll put a little graph down below that tells you what the injected error is. Right.
And you hit the button and inject the error.
Yeah, you can maybe inject lots of different options here. Yeah. But I feel like that's what's missing is right now I've got a tool that tells you when error happens in a game, but you don't yet really know what's good and what's bad.
Do you like having, like when you play games, do you have the frame rate and the 1% lows and all that stuff displayed on your screen?
I do.
Or do you just not think about it?
I do.
Okay.
Just because I'm such a dork, I put it up in the corner where it doesn't bother me. I actually think I get like 3. I have a representation of what mine does. I went crazy. So if you look at PresentMon, I actually allow it to scale. So you can actually change the size of the PresentMon thing.
You can get it big. You can cover the whole screen.
And you can change the text. And so what I normally do is if I have a hotkey that pops up the full size on top of my entire screen thing, I love it. But nobody else does. I don't know.
Well, but I mean, I feel like just showing like the rolling average of 1% lows is great as long as you're really good at video games and you never die, you never load menus, and you never pop up the map, any of the things that take over the full UI and add a massive amount of frame lag for however long those frames are up.
It's true.
But like if you're playing that and you're like, oh man, my 1% lows are garbage all of a sudden. Why is that? And it's just because you died 3 times in a row and you have in that last 60 seconds rolling average or whatever it is they're using. It's not a representative number
it's not.
of the actual gameplay.
It's not. I actually, in the in the present mon that we do, there is the ability to graph the 1% lows.
Okay.
And so it's a real-time graph, and you can change both the averaging window and the display size. So if you want it to go over the last 10 seconds, you can have it over the last 10 seconds. If you make it like very fast sampling, you can see per frame variation of the percent lows, which is pretty cool, right? Because now, and you can actually graph the average, the 99th and the 90th and the 95th percentiles on the same graph, which is really interesting, because at least to me, because now you get like these kind of like waterfalls of badness.
Yeah.
You know,
waterfalls
of badness.
There we go. I like that. The 1% low is waterfalls of badness.
To me, it's like average frame time is really important, and then the average variance from frame to frame is equally.
Yeah, that's. But again, I'm going to claim that we're in a moment in time where people are not yet on board with this.
Yeah, of course.
But animation error gets rid of the percentiles. You don't need percentiles if you have animation error.
Also, but the thing is, though, if you go out and develop an app that we all can use for benchmarking this stuff,
Open
people
source.
are people are going to say, oh no, it's of course it's going to favor Intel GPUs.
Of course it will.
Yeah.
Well, you know, I struggle with that all the time. I would really love you to do it, or you know, Will to do it, or maybe Epic to do it, right? And so what's needed is not me to do it, but I'm just we're going to do it if we have to.
Okay.
All right.
Like the equivalent of the Netflix, you can get the rating for the encoding.
Yeah, I like that.
We've talked about that. All right, here we go. Rapid fire question. Steven Anderson just asked, Tom, are you a PC gamer or a console gamer?
PC all the way, baby.
Oh, wow. Okay, that was easy.
Mouse and keyboard, or gamepad.
Mouse and keyboard.
Do you ever use a gamepad?
I do. I use a gamepad for things like Batman, Arkham Asylum, and things like where you really need
Rocket League.
I don't use it normally. But when I'm playing an RPG, something where you're like a third-person perspective,
couch game versus living
it definitely is a better experience to me.
Okay.
Yeah.
Okay. Flinder Show Liquidar is asking, which department chooses the name for product lines like Panther Lake, Battle Mage, etc.?
That is in our product teams, so that would be CCG in this case.
Okay. Are you in that department?
I am not. I'm an engineer.
Oh, okay.
What does it mean to be an Intel fellow, Tom?
It means that you
Do you get a hat? Like a jaunty hat?
I don't get a jaunty hat.
Okay.
I think it's just that I have a certain skill sets that are useful to more than one project. So think of it like I'm trying to affect things in a bigger way.
Cross line
groups,
synergy.
Cross groups. But
Okay.
it's and I can help quickly organize things.
Gordon would say you're enhancing verticals across the entire organization.
Think of it like the problem that companies like Intel struggle with is chaos. Right, just closure of the plan and communication of what's important, and there's lots of opinions, right? But what helps I think the role that fellows play is that there's less debate, right? There's a little less debate when I'm saying, trust me, I'm pretty sure. People who have worked with me for a couple of years are knowing when I say I'm pretty sure, that means I am sure. But there's a small chance that I could be wrong, but it's small, and
the vibes are good.
Why don't we just get on with it?
Yeah. All right. This is a deep one. I don't know if you can answer this. ERJ says Intel apparently filed patents on using compression mount technology to potentially allow replaceable GDDR and attaching replaceable components directly to the processor substrate. Is there something you can tell us about where that's going or not going?
Wow. I was not aware of that. I do love the idea of compression technology for GDDR, but I don't know anything about productization of that. That seems like a tough nut. Just productizing any kind of memory replacement in a mobile form factor would just be really quite difficult, I think.
I've seen that guy that takes the mill and mills off the old RAM and CPUs.
Yeah, it's possible.
Yeah.
It's possible.
Yeah.
Friend of the show, Ivan R. What is the final boss of real-time graphics? Ray tracing, latency, something else?
I think that the final boss, and again, don't take this as our plan. It's more like it makes sense to me, is that someday we will no longer require a traditional rasterizer, right? And what will happen is the interface between games and the render engine, call it render engine, will become much more about artistic intent rather than triangles, right? So if you can say, is there a better way to communicate artistic intent than a triangle? Yes, there is. There's 100 better ways to do that. And so why is it that our communication with games is talking about textures and triangles? That's old school. And so if we can get away from that concept, there's probably better ways to do rendering in my mind. And so like that's the end game, right? Probably better ways to do rendering, just like there are better ways to review contracts these days. There's better ways to write papers. There's better ways to do research. So in my mind, I kind of say there's some steps along the way that are pretty obvious. One that's obvious is like, we don't need to show you rasterized frames. I know that you want to see them, and maybe we'll have a mode where you can see the rasterized frames.
It's like a toggle, flip back and forth.
Yeah,
kind of like
give me classic mode. But how about if we did an AI that is generating 120 frames all the time, no exceptions. It is perfect. Okay, and what it's doing is it's taking reference frames, however they come. Right, so that means that this whole question of animation error is being settled by the generator. This whole question of lag and prediction is being handled by the generator. And if I can do that better than a rasterizer, then you can dial up your rasterizer up and down if you want more rastered frames, but it's just going to be lower performance.
But what if 40% of those generated frames are lies?
That would be a bad implementation on my side.
Okay.
That would be bad. I would suck in that case.
Okay.
Yeah. So I think there's this whole question of how do we bring the community along on this journey that is less predictable, because right now we're obviously not there.
Yeah.
And that's why our first step is let's be transparent. There's these things that are called rastered frames, and we'll build tools to show everybody everything, and then people will or will not, maybe they will, maybe they won't, prefer the experiences that we can generate with enhancements, right? Think of it like enhancements rather than replacements.
Yeah. The replacement's the eventual goal, though, just to be clear.
Well, it's not the goal. It's just that it's my belief anyway that the experience will be better if we do that. If it turns out that it's not, then we won't.
Yeah. You're not going to put a bunch of silicon on for something nobody's going to use.
Our goal is not to do AI. Our goal is to deliver better experiences. And if we can do that, we will. And if we can't, we don't. We throw out technology all the time. Like there's like throw.
Give us some hard examples, man.
I'll tell you an NVIDIA example. Do you remember SMP from NVIDIA? You probably don't.
Symmetric, the multiple GPUs?
Simultaneous multi-projection.
Oh, yeah, I do remember that one.
Okay, that's a really good idea.
For a demo.
I didn't want to bring that up, Brad, but yes. No, that's a great idea, right? If you think about complex displays, they're multiple surfaces, they're curved. Why don't we just raster to that surface rather than raster to a flat plane? So creating the ability to have multiple reprojected surfaces simultaneously, that's simultaneous multi-projection. That went exactly nowhere. It was complex. It's hard to understand. Yeah, zero.
Okay.
Interesting. Okay. PS1 Freak asks, will NPUs integrated in desktop CPUs ever be helpful for gaming in the future?
All right, I'm sorry. I blacked. I was having soda. What was that?
NPUs in desktop CPUs, will they ever be useful for gaming?
Okay, so this is a great time to talk about software ecosystems. The way software works and the way gaming works is there's a certain platform that has to be available for a developer to use it. Because if you're building software that relies on some particular infrastructure, that's got to be out there. Otherwise, you're wasting your time. It can't be, I'm going to build software and someday the hardware will show up. It's always the hardware shows up first and then software developers use it. So when you think about the NPU, the user for a consumer is usually and most expected to be Microsoft. Okay, because Microsoft is busily.
Oh, they're trying to use it.
They are,
and or sometimes not. Sometimes they're putting it in the cloud.
But again, I say the platform has to be there before the software comes, and so that's what we're doing. We're building Panther Lake, and it's going to allow us to deploy the NPU across millions of devices. So now I think it's, what is our number? Is it 48?
48 tops is the Copilot Plus spec. It seems.
Yeah, and I think you'll look at Panther Lake, and you'll see that it's 50.
Oh, wow.
Okay.
That's two more.
Okay. So what's happening is that platform is now going to be everywhere. And it's mostly going to be, I think, until there's a better solution. Today, there's not a great way to do scheduling on the NPU. So that means that if somebody else is using it, somebody else gets sort of locked out, and so you can't rely on that resource to be available. And so I feel like that's where we are today with the MPU. The MPU is primarily going to be used mostly by Copilot Plus kind of applications, and then over time, other software developers will, develop more. We do a lot of development with like media applications and content creation,
camera stuff.
Yeah. So all that's still going to happen, but the big use of the MPU is for these next generation PC experiences coming from Copilot. Okay. That means that the developers of games don't really have that resource available even after it's deployed.
Yeah. Because Copilot's hogging all the MPUs.
Yeah.
But this is a Microsoft problem to fix, though. Presumably, you could build an API that lets you schedule the MPU.
Yeah, and it's just a question of maybe the features that you disable on your PC experience. Mm-hmm. So it's a problem to be solved. I know they're working on it.
Yeah.
And there's a better hardware scheduling coming for AI workloads on PC, especially because we now have MPU, GPU, and CPU, and you have a network that needs to run. Who does that mapping? Well, we need a scheduler, right? And that's just for one AI task. But there are now many AI tasks that are running on a PC.
Okay. I'm going to go to this one. A friend of the show, Brian's asking, do you have a home lab at home?
I do.
All right. If you do, what kind of stuff do you have on it?
Well, I built a room for myself, so I wish I could. Maybe I could show you a picture. I'll have to dig it up. But I'm a YouTube educated carpenter, so I built my lab from scratch, and I did the plans. I did the whole thing. I love it, and it's got clear eye cedar ceilings and walls. Or I spent forever spackling the walls, but it's got clear cedar on the outside. It's beautiful, and inside of it are 2 benches and then bunches of racks. So the one bench has 2 computers. One is a B580 PC. The other one is an NVIDIA something that I compare against. Then my other bench is my construction bench. So I have a SMT kind of reflow thing.
Oh, wow.
I've got microscopes so that I can do my rework. I've got a solder station. I've got all my breadboards, all my rework area. I'm a real engineer. So yeah.
The real question is, which is your soldering iron? What's your soldering iron?
I have the classic one. It's I don't know the brand, but it's like that big one that's got the separate.
The blue Hako or one of those?
It's like the blue box with the cable, and then you put your little iron there. But I have boxes and boxes of surface mount components because I got really into, because I was doing this thing called an LMT, which is a latency measurement device that Intel ended up making in Toronto, and I could not get the guys to quite do what I wanted. So I said, fuck it, I'm just going to do it myself.
Yeah. Beep.
And so that's when I discovered there's a surface mount technology board manufacturers that you can do online. And yeah. And so I built my own boards, and I've got these piles of, and I said, well, how do you get your components on there? So I got this reflow thing. So yeah, I have a lab and I use it. I got an oscilloscope. I got all this stuff, man.
That's very fun.
Yeah.
Nerd.
Gee, I gotta see if I can dig up. I could show you a picture of it. Yeah.
All right, couple more questions that we can get out of here. There was somebody in the chat. Oh man, it flew by too quick. Asking essentially, do you think Intel should make motherboards again to control? Oh, here it is. No, I lost it. Yeah. So, Gentlestone, friend of the show, Gentlestone. Will Intel ever make motherboards for consumers again? If so, they can enforce quality control.
So I don't know the answer to that.
Do you think they should?
It's hard for me to imagine a scenario that would be a profitable endeavor for Intel, right? Because motherboards are actually very low cost today when ODMs are manufacturing them. So this is like a question about disaggregation and value chains. And there's things that Intel's very good at. And if we do things that we're not very good at, like cost control, that tends to be a less competitive product, which tends to be a loss leader for us. So when we're doing things that are away from our core skill set, like CPUs and GPUs, that kind of stuff, those are usually enabling things. They're things that we have to do because nobody else is doing it. It's not things that we would want to do. So the degree to which that others are willing to specialize and support the ecosystem, it's good for everybody. So I don't expect Intel will come across the need to make motherboards. But if there's ever a blocker there, we certainly would. Yeah. Okay. This reminds me of the AMD back in the day. I don't know if you know this, but NVIDIA used to make chipsets for AMD CPUs. that was Enforce.
Oh, yeah. Yep.
And Enforce got its start primarily by making sort of like no GPU chipsets for AMD, and effectively they became the workstation chipset for AMD. Right now, if you're AMD, you're selling $1,000 CPU. We're selling like a nothing dollar chipset, but every $1,000 CPU needs that nothing dollar chipset. So when things got dicey, we would have supply problems.
Oh, weird. Okay. Any other questions you guys have? I've got one last one.
I'm good to go.
All right.
Good, yeah.
Zaz ask, what's the hot new recipe this year? Last year when you came on, you were talking about
It was pie time.
I have one. It is the best chicken that you can make.
Ooh.
like fried or what? What are we talking about?
It's basically it's a grandma French recipe. So this is, if you are a French grandma, and I don't mean anything bad about that.
Pardon me.
I like French people. I like grandmas. It's called chicken velouté.
Oh yeah.
Have you had it?
It's amazing. In the cone?
No.
Is it that one?
This is it's basically a mustard. It's a mustard gravy, effectively, that you put on baked chicken, but the whole process is easy. It's quick. It's spectacular. It is.
Oh yeah,
it's
looks
like a
good.
Yeah, you see it?
sauce.
You see it?
Tell me more.
I would eat
Yeah.
this.
So basically, you make a roux, and then a little white wine, and then you're kind of thinning out your roux with some stock, and so now you've got basically a gravy. But the trick is you add mustard to it. So you take a little of the gravy out. You're making like a mustard whisk. You add the gravy back, and now you've got a mustard gravy sauce, and you finish it with fresh tarragon.
Nice.
That sounds fabulous.
It is really spectacular.
Nice crispy chin.
It's
skin roast chicken.
It's spectacular. It's spectacular.
Follow-up question, Tom.
Yes.
Where's that pie?
I was going to ask that. Last time you said you'd bring a pie.
Did I say I'd bring it?
You did. Well, now you got to bring
Roll
the
the tape.
roux.
Pie of lies.
The velouté
Roll the
thing.
tape. I
Yeah.
said I'd bring it, huh?
Talked about a deep dish French pie. I
Ooh.
think
I've got a better recipe than that. If we're talking desserts, so there's a place up in Napa called French Laundry, right?
Yeah.
And then right next to French Laundry is
It's
a
a
place
restaurant,
called
not a laundry,
Bouchon.
though.
Bouchon,
Yeah.
right? And Bouchon is like Tom's Keller bistro. It's not as expensive as French Laundry. It's really good stuff. And they have a cookbook. And the cookbook is called Bouchon Cookbook. And in there is a recipe for brownies.
Oh.
Okay. Now, these brownies are the best brownie ever. And it's basically very little flour, a lot of cocoa, and butter. And that's basically the brownie mix with a little bit of other stuff. But it
So it's real chewy.
Dutch. No. It's cakey.
Cakey.
Yeah, it's
interesting.
cakey. Yeah, but it's very, very nice. So if you want to look up a brownie recipe, go there, Bouchon Brownies, as a dessert.
They do a French apple tart where you slice the apples on a mandolin, and then you lay them around vertically around the whole thing, and it's just all apple. It's really, really good.
Spectacular.
You have to alternate the pectin apples and the not pectin apples.
Is that
so
right?
you it's like Granny Smith, then Macintosh or Brayburn or something like that, and it ends up like a gelatinous apple goo, and it's really good. Highly recommended.
All right, that's what you get. That's what you get.
Intel brownies. Yeah. I'll talk to Nick. He'll bring them next time.
Nice.
Anyway, that was it. That was the show. Let's wrap it up here. Check back next week for your fix of PC Talk here on the Full Nerd. If you want to tune in to these live shows, you can subscribe over on the Full Nerd Network YouTube channel. We're live every Tuesday at 11 a.m. ish. Yeah, you can come into the chat. You can hang out. But don't worry, you can catch us on the go. If you want to listen to the podcast version, the audio-only version, find the podcast any cool app that you can point your RSS feed to. Not only that, if you just like to read, there's people out there who like
Words
to read.
printed on a page?
We have
Wow.
a Full Nerd newsletter. Did you know this?
I did not know
One
that.
Eleni E writes every week, every Friday morning, you can get a freshly baked Full Nerd newsletter into your inbox. You can sign up for that at PCWorld.com/newsletters with an S /sign up. And sign up for that newsletter. It's really good.
Last week
at
you
it.
talked about the end of Windows 10.
Yeah, and Brad tag teamed. Brad wrote half of it too. It was pretty good. Yeah, good stuff. So I want to thank my co-host Brad for staying late. I appreciate it.
Hey, Brad.
Yeah, of course.
Good to see you.
And keeping the ship
You,
going. Will, thank you for bringing
pleasure.
the game dev knowledge.
Love it.
It's hard earned, blood, sweat, and tears in the trenches out there.
It's important. It's good. And thank you, Tom, for coming by, especially without any handlers. There's no lawyers.
No lawyers
There's no
in the room.
PR people. You did.
Did I say anything terrible?
No, yeah, I think you did. I think you did great. You should come back.
Yeah.
Just anytime Nick's on vacation, you should come by.
I mean,
Hi.
yeah. I mean,
Thanks, Adam. It's good
and
to see you.
yeah,
Shout out to Nick.
always good to
Appreciate
chat with you. Thank you for coming in, especially in the studio. It's always fun. Thanks everybody for tuning in. Catch us next week. And Willis, thanks for controlling the verticals and horizontals, however complicated
job.
they are. Let's take us out of here.
Alrighty. Thank you, everyone, for tuning in. Thank you, Tom, for stopping by. I'm going to have to get that recipe from you post-show here. So thank you, everyone. We'll see you next time. Bye.
Bye.